Hello, everyone. A very warm welcome to IEAGHG's AI in CCUS workshop. We are very happy to have you all with us today. And we will start with a bit of background to IEAGHG. For those of you who do not know who we are or what we are doing in particular, my colleague Abdul'Aziz will now give you a couple of minutes overview about our activities.
Right. I imagine you can all see my screen. So once again, welcome to the IEAGHG AI in CCUS workshop. My name is Abdul'Aziz again, and I am pleased to run through a few slides to say a word or two about IEAGHG. So we are a technology collaboration program and are part of the IES Energy Technology Network. However, our views, findings, and publications of the IEAGHG do not necessarily represent the views or policies of the IEA Secretariat or its individual member countries. So the IEAGHG, we are at the forefront of CCUS research. We advance technology that reduces carbon emissions and accelerates the deployment of CCUS and CDR projects globally. This slide shows the membership of the IEAGHG. Our members represent a broad spectrum of stakeholders from around the world, including governments, the industry, and technology developers. Their support is critical to our mission of advancing understanding and deployment of greenhouse gas mitigation technologies, particularly carbon capture and storage. Through their collaboration, IEAGHG is able to deliver independent, internationally recognized technical studies, workshops, and knowledge-sharing activities. We are grateful for the continued commitment of our members, whose expertise and engagement help ensure that our work remains practical, impactful, and aligned with real-world challenges. This slide showcases some of the activities undertaken by IEAGHG. However, due to time constraints, I won't be able to walk through all of them in detail, but I'd like to highlight a few. First, IEAGHG produces a broad spectrum of technical reports. These are not policy prescriptive, but they are policy relevant, supporting evidence-based decision-making across the CCS landscape. IEAGHG is also the organizer of the world's leading conference on carbon capture and storage, the GHGT series. The next GHGT conference is scheduled to take place in Australia next year. In addition, IEAGHG also runs the CCS Summer School, a fantastic opportunity for early career researchers to deepen their understanding of CCS. I've always been proud to be an alumnus of the program myself. The next summer school is scheduled for July in Canada. I also wish to note that IEAGHG is the custodian of the Post-Combustion Capture Conference, which is now entering its 8th edition. The next conference is scheduled to take place this September in the beautiful city of Marseille in France. And we're pleased to have Total Energies as both co-organizer and host for this event. Registration will open in June, and we look forward to welcoming participants from across the CCS community. Before we get started, just a few quick housekeeping points. First, we will take questions at the end of each presentation, so please feel free to post your questions in the chat as they come to mind, and we will endeavor to come back to them during the Q&A sessions. A recording of the workshop will also be made available after the event. And lastly, but not the least, due to cancellation of one of our speakers, please note that the break will now run from 15 British Summertime BST to 3:30 BST. So thank you for your time, and we look forward to a productive and engaging workshop. If you have any questions related to the workshop, you may kindly contact Jasmin, Kemper, or myself. On this note, I'm pleased to ask Jasmin Kemper to take us forward from this point. Thank you.
Yes, thank you, Abdul'Aziz, for the introduction to what we are doing. And yeah, we are always happy if you want to reach out to connect with us and get networking activities starting. So feel free to contact us via all of our channels, email, LinkedIn, and so forth. And so the main aim of this workshop today is to foster understanding for the use of artificial intelligence in carbon capture, utilization, and storage. And we want to focus today on the fact-finding and reviewing what is the current status of AI and CCUS with some case studies showcasing where it is used. And there we will have all of our lovely speakers today telling you about how they are including AI in their daily activities. And so we wanna have kind of a fact check what AI can bring to the table today, and maybe have some discussion what could it potentially bring to the table in the future. So with great pleasure, it is now that I can introduce our first speaker today, Julio Friedmann from Carbon Direct. Julio will tell us a bit more about the opportunities and challenges of AI in CCUS. And he will set the scene for this workshop by relying on insights from the recent ICEF roadmap. Julio, the floor is yours.
Thank you so much. It is a delight to be here. Thank you. Thank you, Jasmin. Thank you, Abdul'Aziz. Thank you, Tim. Thank you all for being here. I will give a short presentation so that we have lots of time for question and answer. Let me start by saying that this work was supported by the Innovation for a Cool Earth Forum, ICEF, and specifically this event and this publication pathway is supported by the Ministry of Economy, Trade and Industry in Japan, and by their innovation arm, NIDO. My co-authors include David Sandalow, Colin McCormick, Alp Kukuchel-Beer, many of whom you may already know. So let's just do a quick overview of what AI is, so we're all on the same page. AI is basically the science of making computers perform complex tasks. It commonly falls into 4 different kinds of work. One of them is detection. In this context, you are probably familiar with facial recognition technology. AI is good at that. One application in energy and climate is methane detection. It's basically the same kind of algorithms. A second pathway or use for AI is in prediction. This is effectively what ChatGPT is. It predicts the next word and the next word and makes generative AI that way. Things like weather prediction using AI are an example of prediction. Let me say the weather prediction tools have gotten quite good. We now have 15-day forecasts that are extremely reliable based on AI, as opposed to the kind of forward physics-based models, which you're familiar with from the past. A third way in which people use AI is to optimize. If you take a road trip and you use Google Maps, it will optimize. It will optimize first for time. After that, it may optimize for fees and fares. It may optimize for footprint, etc. If you want to use AI to integrate more renewables into power systems, then you're using an optimization function. The fourth thing that AI typically performs is simulation. If you've played some of these more advanced video games, you're using AI and it is simulating the different actors and agents in the game When you do material discovery using AI, for example, you want new battery chemistries, you are also using the simulation capabilities. Today, I'm going to focus my attention on how you can use this extraordinary set of tools for carbon capture and storage and use. CCUS is important. We are here because we believe that's true. So let's talk about the 7 things that I believe AI can do to improve and accelerate the deployment of CCUS. The one that gets a lot of attention today is material discovery. Finding new materials using AI is a kind of a layup. And people have been doing that for the better part of 10 or 12 years now, using these quantum electromechanic calculations to discover new materials. In this case, we're talking primarily about things like sorbents and solvents for the capture of CO2, but you may also use this, for example, for new electrocatalysts that can be used for CO2 conversion. All of these new materials play an important role in CCUS. All of them can only be found through these applications of AI. In addition to discovering these materials, ranking and screening these materials is another application of AI. Second thing is the design of new reactors. You can actually, again, use AI to not just improve an existing, say, gasifier or an existing stripper column. You can actually make whole new reactors to convert CO2, to capture CO2, etc. And the design of these things in terms of its form, function, weight, material inputs, and so forth, all of this can be optimized and improved using AI. The third thing that you can do is to actually operate facilities or to retrofit existing facilities. Here you're using AI in a somewhat different mode than these simulation or optimization tools. For example, you can make digital twins of a facility and use those digital twins to integrate carbon capture technology into them. You can use AI to operate the sensors and controls in those facilities so that they can detect faults early or detect misalignments between the expected and the real operation of some plant somewhere. Those first 3 are really focused on capture and getting more capture systems out there. And this is true whether you are an entrepreneur making a brand new capture technology or whether you are an asset owner retrofitting, say, a steel mill or a chemical plant. But I don't want to leave transportation and storage off the map because they are important. An obvious way in which you can use AI, and people are already using AI, is around transportation optimization. Sometimes this involves the routing of pipelines. In this case, you may be optimizing for cost. You may also optimize for community impact. You may optimize for environmental risks. And so you can use these AI tools to find different pathways to build a pipeline network. The same thing would be true if you were moving by CO2 by barge or by rail or by truck. Once you've transported the CO2, of course, you are at storage. And there are 2 big applications for AI in storage. The first one is discovery and characterization. If you are in a green field, this is very useful because you may not have a whole lot of data. So you can actually do a better job of characterizing that given using AI to gather data that is in the literature or data that is hard to find to improve your characterization. It is also true in terms of discovery. Here, the discovery may be actually like, where is the best site and how do I rank 50 or 100 sites? It may also be, hey, what really I need to understand is I need to know the pore volume access. How can I use AI to identify those opportunities? Once you actually have a storage site, the operation of the storage site, AI is great for these kind of E-field and I-field applications. Like with the existing facility, you can make a digital twin of the subsurface. You can operate the sensors or controls. You can find places where there is a mismatch, whether that is in terms of pressure or CO2 breakthrough in a field, etc. The last and a very important application for AI and CCUS is on the non-technical parts. Permitting is an important one. Regulation and oversight is a second. Helping the public understand, get better public acceptance, getting better community benefits. All of these are also good tools for AI. And we are already starting to see more and more groups use AI to work in these arenas as well as in the technical ones. Our report made a whole set of recommendations, and many of these recommendations focused on things like policy and workforce. But let me start back a little bit. In order for AI to work, it needs data. Getting data access is critically important to making sure these AI tools succeed and minimize risk and bias and hallucination. This sounds like it's easy. If you're in Canada, all subsurface data is publicly available. If you're at universities, you may have access to tens of thousands of novel materials that sit in libraries in various places. That is not, however, uniformly the case. You may often have proprietary data from an asset owner. You may have land use data, which is not publicly permittable. In many cases, there are sensitive kinds of data. Those are important to have access to train the models. And policy is actually really important to figuring out the right way to get access to data, say geological data in China or something like that. How can you get access to that data in a way that preserves the security and integrity of the data, that preserves the needs of a population, but also does a good job? I mentioned a risk already, which is data bias. For example, there's pretty good geological subsurface data in most parts of the United States. Might not be the case in Nigeria, might not be the case in India. As a consequence, you may actually have real bias in the AI because they don't have enough data or the right kinds of data to give you the right kind of answer. I'm sure we have all seen the hallucinations that you get out of these generative chatbots and so forth. You don't want that sort of thing if you're operating a carbon capture facility. You need to make sure that the data are unbiased so that the AI can do their job well. I mentioned workforce a second ago. We need training in the workforce at all levels. Yes, we need more coders. Yes, we need more algorithm developers. Yes, we need more specialists working with them so that that gets done well. We also need very basic level understanding of what AI is and how to use it. That especially is important at all levels in government. Business seems to be doing a pretty good job of pushing this along, but if you're a regulator, if you're a congressman or a legislator, you need to understand the capabilities of AI. You also need to understand the limits of AI so that you can use it appropriately and make and support key policies. We recommended specifically that in all government agencies dealing with climate and energy, including those dealing with CCUS, they have an AI officer whose job it is to identify opportunities to make sure that the workforce is trained, to make sure they're working correctly and well. A last recommendation that we made is that in many cases, we have people who are subject matter experts, say at CCUS. We have people who are subject matter experts at AI and AI design and operation. These two groups of people basically never talk. We need to find ways for governments and industry to work collaboratively to pull these groups together. If they pull their groups together, then in fact, there's a better chance that we will have better outcomes. And in fact, just that bridge building and convening hugely important set of tasks, if only there were a group like IEAGHG that did such things. I've talked this whole time about how AI can enable CCUS. I would be remiss if I didn't also mention how CCUS can enable AI. We are seeing many groups out there building uncontrolled natural gas plants, especially in the United States, increasing the capacity factor of existing natural gas plants. Obviously, these increase the emissions loads. Many people are worried about lock-in. CCUS is the opposite of lock-in. It undoes the emissions from an asset. We have seen announcements like ExxonMobil's recent announcement with Calpine, the fact that they are creating a vertically integrated business offering in which they do the capture, the transportation, and the storage. Those could get more AI and data center facilities on the field. Similar sort of thing with the GE Verona Chevron engine number 1 offering. We have seen companies like Meta announce very large facilities in places like Louisiana, 2.6 gigawatts, $10 billion of investment. That is a good target for CCUS, and I'm pleased to say that they are thinking along those lines already. The government of Louisiana is engaging on that front with the utility, with Meta, with many parties. It is true that all hyperscalers need speed to market. That's why they're building uncontrolled natural gas, because it's the fastest thing they can do. They are not as sensitive to price. They need speed first. So probably a lot of retrofit opportunities in these cases, as opposed to born integrated. It is the case that they are all seeking, all the hyperscalers, all the tech companies, their partners, the people who build the data centers, the people who operate the data centers, the people who permit the data centers, they are seeking to understand CCS as an option to decarbonize the power supplies. It has been my experience and Carbon Direct's experience that all of our customers still care very prominently about their climate commitments. They are not backing down, they are doubling down. And we are pleased to see this kind of focus. I expect that many of you out there are starting to see uptake in CCS for AI applications. With that, I'm going to pause. I think we are in a position where we can take questions from the audience as we go. Jasmin, Abdul'Aziz, I don't know how you'd like to proceed, but
yes, yeah, thank you very
go.
much for setting the scene, Julio. So if anyone has any questions or comments, or it's not just asking questions, but also maybe sharing your experience, then please post it in the chat, because I think I've not seen any questions so far. So maybe I'll start with...
Thank you, Jasmin, for posting the link to the study.
Yes, I thought that might be very, because as you didn't have slides, some people who are more visually oriented might want to have a look at the material in the roadmap. There's one dedicated chapter on CCUS. The roadmap itself, it's about AI in climate change in general.
Mm-hmm.
And yeah, as I said, one dedicated chapter on
Right.
CCUS technology. So considering...
Unsurprisingly, I wrote that chapter, so I feel like I'm a pretty good source on this. Thank you, Jasmin. Sorry to interrupt.
Yes, yeah, no worries. What one of my questions would be, because if I'm correct, this was already the second roadmap on AI that the ICEF has done. So are there any efforts in making this into a constant series that you say, oh, we are looking every so often at how it has progressed? Or was that just more like a coincidence?
So let me speak just a minute about the Innovation for a Cool Earth Forum. This was actually started by Prime Minister Shinzo Abe when he became Prime Minister 11 or 12 years ago. He wanted to have a technology and climate program that put Japanese climate technology on the map, and ICEF was born. Among other things, there is a secretariat whose job it is to every year produce roadmaps. And that process is reviewed by the directors of the ICEF itself. And so every year there's a new proposal. The first year we did AI, people were very enthusiastic about it. They said, please do that again, because just over that 1 year, so much had changed that people realized it was important. We went from a 100-page report to a 350-page report, so it is quite detailed and in-depth. This year, we are not going to do AI again, and my guess is that the next year we will not do AI again either. There's just other topics to do. Producing these reports is quite a lot of work. I will say, though, that this year, the subject that we are almost certainly going to take on is sustainable data centers. In addition to AI itself, part of the question is how do you build and operate these things in a sustainable way? And we're doing the whole kit and caboodle. We're doing everything from the Scope 3 emissions around cement and steel and chips to the power itself, to the water consumption, their siting, cooling options, etc. So those reports come out every year, the first week of October. That's when the ICEF event is. After that, that's a draft review for public comment. We eagerly await people's comments, and we would love to see people at COP30. We actually do the formal release of each report at a conference of the parties. So in Belém in November, hope to see you there.
All right, and we now have a question in the chat. So someone is asking, what about the risk on relying too much on AI? So especially regards the lack of trust from the stakeholders, especially, I mean, we see AI, especially generative AI like ChatGPT hitting the news almost every day now, and people are getting skeptical and are not trusting because of those hallucinations that have been shown. So maybe you can comment on that.
Yes. So let's start by saying media over indexes on these things. People are like, I don't trust ChatGPT, but they still use it. You know, there is in fact a risk, not of necessarily over relying too much on AI, but AI comes with risks. There are biases problems, there are hallucination problems, there are quality concerns. The place where I actually worry about the over relying is not in the public acceptance, but rather in policymakers jumping to conclusions based on faulty AI and driving too far and too fast with what could be a poor product. The solution to this is attention. That's part of the reason why we so strongly recommend training to people and why we think having access to the data is so important, so that it minimizes the risk of bias and fault. I would add here that the people who say they distrust AI already use it in many, many fields and they don't even know it. So what people are really saying is that I don't want to lose my job, or I don't want this chat bot to get rid of creatives who I like. Those are real problems and they're real challenges. So it's a risk. The only way you manage a risk is by managing it.
Thank you. And we've got a couple of more comments and questions. So someone is asking whether you can offer thoughts on developing digital twins for green storage sites, which are typically limited by the availability of characterization data and historical monitoring data.
Yeah, so groups already do this. This is something we mention in the report. It is unclear today whether or not AI will increase or decrease the use of fossil fuels. The energy companies have put billions and billions of dollars into developing AI specifically to optimize production. They are trying to minimize the well costs. They have put sensors and controls in existing or new oil fields. So those applications already exist in the subsurface. So it's kind of straightforward to translate those same tools into exploration and production applications, but for carbon capture and storage in the subsurface. One of the things about a digital twin in the subsurface is you're dealing with a lot more uncertainty than you are using, say, for a boiler retrofit, where you know the dimensions of the boiler to great precision. You don't know that in the subsurface. So conventionally, you will be tying that to some kind of optimization function as well, where you are regularly updating the static geological model, you are regularly updating the flow models in your digital twin based on new information as it comes in. But this is actually incredibly powerful to reduce the risk of failure, to reduce and manage the uncertainty in the subsurface. I would add that this is actually a very useful tool already for planning and drilling a well. If you're in a greenfield and you're not quite sure about where to put it or what might happen, like the AI can be useful. Again, you have to be careful because you are at risk for error and bias because of the lack of data. I'm dealing with this like in real time. We have a customer who's trying to develop a greenfield CCS project, and the data availability in their one site is quite limited. So the question is, what data can you use to develop an AI to reduce the risk of a bad well? Wells are expensive. You want the first one to be good.
Yes, some more thoughts from the chat is wondering whether anyone has done a study on the comparison on the help AI can do for CCS versus the emissions generated for its energy consumption.
Right. So this one is easy. And actually, we have a whole chapter on the energy consumption of AI. That's chapter 15 in the report. I would encourage you to look at it. There are different kinds of AI. They have different kinds of energy consumption. So the training phase is often the one that is most intensive, but query is use phase nowhere close. It is often parroted in the public sphere that an AI-based query uses 300 times the energy of Google searches. That is incorrect. It is not true. And in fact, actually, for any of these climate applications that we talk about, the likelihood that they can substantially reduce emissions compared to the actual energy use of AI today is pretty clear. What is also the case is that the energy consumption associated with AI is growing. But that is growing for all kinds of things. Let me start by saying energy demand growth, only a quarter of it is for data centers. A lot of the rest of it is for electrification. A lot of the rest of it is for onshoring of new domestic industries. Like there are many new demands for electricity, including things like vehicle electrification, which clearly reduce emissions. Out of the data centers that are coming in, only about 40% of that is AI. So our finding is that today, at least, AI uses less than 1% of global energy and probably uses much, much less than 1% of global energy. That is rising. It is also the case that most of the energy going into these AIs is green. The hyperscalers are trying to find as much nuclear renewable energy as they possibly can, so the energy consumption doesn't tie directly to emissions. There isn't a direct connection, even in the cases of these uncontrolled plants. So if you have like a big facility that's emitting 5 million tons a year of CO2, and you can use AI to retrofit it with CCUS, do it. You are getting from a factor of 50 to 500 times emissions reduction than the AI energy consumption itself.
Yes, that's an interesting topic that also comes out because we organize big conferences, right? As some of you know, the GHGT conference, and the last one had more than 1,500 attendees, and those also have an impact. And especially after COVID, sometimes we are asked, but how can you still have in-person meetings when you could just have it virtually? And this causes people having to fly around the world. But if you see that in context, we noticed that during our one virtual GHGT conference that we organized, we sent surveys after, and we noticed there weren't any projects going forward or being accelerated during COVID because of us only meeting virtual. Whereas when we look at other conference, the conference might have a footprint of some 800 tons CO2. So we always do a carbon footprint of our conferences. But if you put that in perspective, one project capturing 100 tons a day, right, going forward and getting off the ground. I mean, it's not like the free ticket an excuse to not think about how many conferences you should attend, but it also shows you that those projects are only happening and are only happening faster if we meet in person. And similar might be interesting when we get to our permitting presentation, and because that's currently a bottleneck that takes very long and is in getting CCS projects off the ground, right?
Right. So let me also just give some facts to calibrate people. People aren't automatically experts at this, so it's a reasonable question. You know, what am I actually doing here? If you compare, say, a query versus making an image versus making a video on AI, the query is basically almost zero energy consumption. The image generation is like 100 times more than that, but it's still quite small. But the video might be 500 times more than that. So making a video is way more energy consuming than just making a query. So again, the kind of AI, the way that you use it matters quite a lot. Even in that case, that is about making an AI video is about the same energy consumption as running an air conditioner for an hour. It is and using conventional queries is many factors smaller than just charging people's cell phones. You have to calibrate for actual energy consumption in the world. So we have a question here. Go ahead.
Yeah, it says, maybe let's do the specific one on the roadmap. What specific AI innovations highlighted in the ICEF roadmap show the most promise for reducing cost and improving the feasibility of CCUS deployment? And how does the roadmap balance short-term implementation versus challenges with longer-term AI-driven advancement to meet net zero targets?
Yeah, it's really not possible to answer that question. The future is opaque. We are at the very earliest stages of doing this. I can offer, though, at least one example that is forward in my mind. When I was in government, I had the good fortune of trying to get the Kemper project up and running. That ended up being a $7 billion write-off. If AI could have avoided that, that would have been worth a whole lot. We often think about these things in the context of how much efficiency gain can you get, or how much energy use can you reduce, or can you reduce the capital cost by value engineering. Like those are straightforward quantitative metrics. But it's very hard to say like this would have avoided a bad outcome, or this would have enabled a plant to get built that wouldn't have gotten built. Like we can't answer these questions today. People are trying, they're doing their best, but it's a little early to answer that question quantitatively.
And then there's another question. Are you familiar with the usage of retrieval augmented generation in order to ground LLMs within a body of knowledge in order to prevent those hallucinations?
Yes, and in fact, because hallucinations are a real problem, unsurprisingly, the industry has put a whole lot of effort into making them better. One of the things I found hilarious is that people are starting to use different chatbots to review the work of other chatbots. So if something that comes out of Claude will then go through ChatGPT to review for look of hallucination. This is hilariously peer review to me. But be that as it may, people are getting better at all of these tools. And I am pleased to say that the innovative approaches to reducing and managing hallucinations, it really does start with data and data access, but the algorithms are getting better at such things. So you should expect that the large language models are getting better. These things are not the application space is not keeping track with this. Like lawyers should be using this stuff a whole lot more than they are to review legal documents, to draft legal documents, etc. If you're preparing a regulation, like a Class 6 well application, that's hundreds and hundreds of pages, but about 80% of it is boilerplate. We should be using these generative AI tools to speed that along. And there's also very specific aspects of it where we should be doing better. It can be very expensive to actually generate a subsurface model and run it by hand. We build these things bit by bit. We run them in supercomputers. Like the AI could actually speed that process, provided it gives you the same kind of fidelity that the ancestral models would. The last thing I'll say is we are starting to get to the point where regulators and policymakers understand the value of using AI to review documents too. I'm sure everybody here has at some point or another thrown 10 technical papers into a chat bot and said, please summarize and compare these papers. What are the key findings? Like that's incredibly valuable stuff. And it happens in like a minute and a half, as opposed to, you reading for a week. So we should be thinking about the appropriate way to use these things to review regulation. So again, that step can go more quickly. I look forward to the day when we have way too many applications to manage compared to the workforce, and the AI can become an enabling tool to speed things along.
Yes, and then maybe one last question that probably also cuts into the legal aspect. For example, someone's asking if you have a new reactor design, would you have to go through pilot and demo testing before you could recommend the AI design for construction? And what are the legal implications if you, using AI in your research now? And
unquestionably, and I think we are pretty far away from a future where a novel reactor design in the AI goes straight to field. Like, no, I don't think we're close to that. What I do know is the people who are building these new reactors actually design them in the computer. They use the AI to discover and to optimize, and then they will build their reactor in the lab. They'll still start at the benchtop or the high bay, and they'll do these things, and they'll kick the bugs out of it because the real world is still not the chatbot. If they're smart, they will also then use those findings to put them back, to put the inputs back into the AI to come up with a better reactor to design, but it will still have to be tested in a large pilot before it gets tested in a demo. We are not yet at the point where the AI are sufficiently reliable and proven to speed the physical testing of these things. So those are still necessary and important steps. It may come to the point where you can start doing that, where right now it's typical that if you have a new design of anything, you're typically looking at a factor of 10 jump. So something that's 100 tons a day goes to 1,000 tons a day, goes to 10,000 tons a day. Like you scale on projects and that kind of an order of magnitude every iteration. It may be that we can start going faster and better than that, but to date, no, you still need to do the hard work of building and testing. What the AI can really help you do, though, and I'm going to close with this, people sort of think about these things as incremental improvements. We can get another 10% efficiency out of this. For me, the real value here, and the reason it's so hard to quantify the benefits, is for the curve jumping stuff, where you come up with a completely new kind of reactor that is wildly more efficient, or wildly more productive, or wildly less energy intensive, so that you're not looking at the incremental benefits, you're looking at a very large benefits. We have seen that already happen with the materials, where these novel materials can give you substantially better performance, not incremental performance. These curve jumping sort of things will also matter for like corrosion resistant alloys, new kinds of photocatalysts, like all this stuff. We are just getting into this. And I would encourage you to think not just in terms of how I can save time or how much I can save money, but how I can discover really big new opportunities that I could not have seen before. With that, it has been a joy sharing some ideas with you this morning. Thank you again.
Thank you very much, Julio. It was lovely to have you on.
And I wish everybody a good couple of days.
Yes, thank you. So next up in the agenda, we would have, according to the plan, Aliyu from Argonne National Lab. However, unfortunately, he does not seem to be online yet. We have emailed him, but we have not received any reply, whether he has technical issues or whatsoever. Luckily, Jeroen Snippe and Sarah Minicini, who have the next presentation, have agreed to jump in and do their presentation first while we are trying to get a hold of Aliyu. So, Jeroen, if you are ready to turn your camera on and share your screen.
Yes, hello, Jasmin. I just switched my camera on, and I hope you can hear me.
Yes, we can see you. I can hear you. Yeah.
Excellent. Then I'll also share my screen. Do you see a presentation coming up?
Not yet, but we have a large meeting, so it might take a couple of seconds to come through.
Here we go again.
Yeah, now it seems to be coming through. Yeah, I can see it now. Yeah.
Yes. Okay. Yes. Thank you for the introduction.
Yes.
Yeah, so my name is Jeroen Snippe. I'm a reservoir engineer at Shell, also a subject matter expert in CO2 storage. Sarah Minicini is also on the call, but given the short time for the presentation, we decided that we wouldn't be switching presenters. She will be helping answering questions if needed. And then there's many other people who contributed to this material in this presentation. I would like to thank. Yeah, unfortunately, in Shell presentations, we always need to flash by this legal note, which luckily I'm not supposed to read, but it's essentially saying you should not sell or buy any Shell shares based on this presentation. In terms of technical contents, I'd like to cover 3 examples from Shell. I would like to point out that at least for the first one, which one that I'm most actively working on, we actually do have very good collaboration between CCS experts like myself and AI and digital experts in in other parts of Shell. So that link has been made, at least internally. What I will talk about is a tool about plume migration prediction that we are now rolling out for stored site screening, so for early stages of project maturation. I'll talk a bit about a containment tool for legacy well integrity assessment. And I'll say a little bit about monitoring, which is Sarah's topic. And Sarah, feel free to jump in if needed. Jumping straight then into the plume migration screening. As already alluded to, well, this is an application area where we try to replace in parts physics-based conventional simulations. The problem with those is that even at site screening stage, when our models are very simple still, typically so-called shoebox models, given the grid sizes that we need even in those models, the run times can easily be hours, up to a day maybe. And that especially when you are applying this to early screening stage, when your subsurface uncertainty is still large and you want to screen many realizations, this is really the bottleneck or a bottleneck. So for that reason, we have trained an AI tool. This was using the same framework and partly based on work done at Stanford, between Stanford and NVIDIA. And for this, we also collaborate with NVIDIA. So GGWN at Stanford was building a tool called CCSNet that I guess some of you are familiar with. We have adapted similar strategy, but to tune a tool like that more towards the needs as we see them. So how do we do that? Just in short, so the underlying AI technology, and I won't go into any detail, is so-called Fourier neural operator. Essentially, it needs training. We train it by direct numerical simulations, so maybe about 5,000 or 10,000 of them. Then we train the model. We also have many direct simulations for blind testing, and based on that, we may further train the model until we have sort of convergence. Then we have a final model, and that we can roll out to product teams who can run it by themselves. I should mention that what we use here is that we don't only model the injection period, but also post-injection migrational period up to 1,000 years. And that's important to understand how far your plume can migrate, given the limitations of these models, though. Since the number of parameters in subsurface is essentially infinite, you need to limit them before you can train anything. And for that, we just did a conventional tornado analysis, and in the end came up with, in this case, 16 parameters, including like reservoir permeability. Our model is similar to models we would use if we would use direct numerical simulation at early screening. So it's shoebox models. So you see a 3D view, you see a cross section. It's just a flat top surface. It does have layering. It has a dip angle because that's important control on migration. But typically we visualize flattened on the top surface, so without a dip angle. And that's something I'd like to point out because at some point, typically the model is like 100 kilometers long, will intersect like ground level. And in the underlying simulation, we just make that part inactive. But that means that CO2 can start accumulating at this plane that after flattening becomes sort of a line. Then it's not realistic anymore, but it's indicative of a plume, just essentially lack of containment that would migrate so far that you don't have containment anymore. Here you see type of results we generate. So like mass of CO2 distribution, gas saturation, and also pressures. These are examples of training and validation, or actually validation on blind tests. So after training, here you see in cross-section just arbitrary permeability fields on a log scale. And here you see the simulation results for the blind test against the prediction of the trained AI tool. It's not a perfect match, then the question is it good enough? For that, we typically also do create derived metrics, like the vertically integrated mass profiles that you see here, where in black is from the direct numerical simulation, and the red curve is the blind FNO prediction. And the reason that we are more interested in that than the exact shape of the plume often is that your risk profile, if you now integrate this type of work with site development, and especially risk assessment, you are very much interested in that mass distribution more than the exact position of the tip, because there's just very little CO2 at the tip. Okay. In other cases, so here the matches are reasonable. There are some cases where it's not that good. And the question is that problematic or not? So we first looked at that, and that's just part of the validation aspect in a statistical sense. So this is, I think, with about 3,000 validation cases or test cases. And we just look at for plume migration distance, direct numerical simulation versus AI prediction. And as this is for different time snapshots, end of injection to 1,000 years post-injection. And then you see there's reasonable R-squared values, but there are outliers, and for the pressure it's somewhat better. Now, yeah, if you apply now this tool in prediction mode, you of course don't want to be in one of those outliers, and it's hard to know if you would be without also doing the direct numerical simulation. So we were a bit worried about that, but then we started evaluating this in uncertainty space, because in the end you want to apply it for a certain site where all these parameters still have certain uncertainty ranges, while this is the view for the global data set, where we just have trained it on very wide ranges of permeability, etc. If we now apply it to a specific site under uncertainty, and we have like a base case, but then 100 realizations where we just vary the input parameters within the limitations of that site, or within the uncertainty ranges for that site, we get very good matches between the direct numerical simulation versus AI prediction. Like this again is plume distance as function of time. This is the mass distribution as function of space at the end of 1,000 years period. And also in statistical sense, so the solid curve is the mean, the grayed area is 1 standard deviation, and this is 2 standard deviations. So that led us to believe that this tool is actually applicable if you use it for uncertainty screening. Then the last slide on this element is how beneficial is it? Well, direct numerical simulation, at least for the grid size we ran, took about 8 hours. After training the model on this GPU node, a forecast on this GPU node is only 0.18 seconds, so you have a factor of 100,000 speed up. But of course, you also need to train the model. So the main bottleneck in training the model is actually that you need to have many direct simulations to train it, like 10,000 or something. So that takes lots of time, but of course you do it in parallel. The machine learning training is not that long compared to that. And then the inference, once you have trained it and do a forward prediction, it takes 1 hour if you do it on 20,000 samples. And that is, including the training time, you already then have slight benefits over direct numerical simulation. But then the point is that this tool is globally applicable, so we don't need to retrain it for a new site. So we get this speed up of factor of 100,000 time and time again. And in the end, we believe this will be very beneficial in achieving a speed up in early characterization of sites. There is future work, like further optimizing, but also adding more realism. Especially we want to add non-flat top map surfaces, because that's important to control on the plume migration distance. Okay, quickly going to the second topic. This legacy well integrity assessment. So setting the scene on this slide. So what's it needed for? Well, the previous work is more about CO2 plume migration, but then as the CO2 plume migrates, it can potentially hit all sort of potential leakage points. And the typically the biggest threat for leakage is from wells, and not so much the injector itself, but old legacy wells that may be, for example, 80 years old or whatever. And you don't always know if they can stand, if they're not potential leakage paths. So that's of course also according to regulations something you need to investigate very carefully and remediate these wells if needed. And that the workflow for that, the conventional one, is just identify all the well locations in your plume area or expected plume area, but also outside the plume area, because the pressure can also lead to its own risks, namely brine contamination of shallow groundwater. Within that, look at all the status of all these legacy wells and create so-called well status diagrams that says a lot about how they have been abandoned, so how much risk of leakage there is, and then also visualizing that in the context of geology, generating so-called plumbing diagram, and in the end it all feeds into a bow tie or risk assessment, so a bow tie risk assessment typically of the entire project, what sort of monitoring you need to do and which wells you would need to remediate. Now in this area, we have started trying to automate that using machine learning, using existing techniques, but chaining them together according to this workflow as much as possible. I mean, from a user perspective, the problem statement is that if you do this manually, the process I just described, if it's really like 100 wells, is very tedious and it takes a lot of time. And then a solution consists of many components. One is, sometimes even the old well files, they are not even digitized. They might even be handwritten. So there's things like OCR, so optical character recognition, and then you need to recognize keywords in here that have to do with the well abandonment status. So for that you need to have natural language processing that can be either rule-based, but also generative AI, of course. And then in the end, generate these plumbing diagrams. So we have a preliminary tool. The user interface looks pretty simple still, but anyway, there's a screen where you can drag and drop or upload your well files from your database. Then there's a component where the well status diagram is generated and integrated with your geology. But very important is also user edit loop, because this tool speeds up the conventional workflow, but it can still be error prone. And definitely when it comes to containment of CO2, we don't want any errors. So it does need careful user edit. Nevertheless, there's still an overall speed up, but the better, of course, the AI part would be, the less user intervention you would need, the more speed up you would have. In the end, it generates these well plumbing diagrams with, like here in green, your storage reservoir, here, like in blue, your shallow groundwater potable aquifer, and then these well status diagrams showing things like cement plugs that are all automatically extracted from file, and risk identification. Okay, I don't want to go further in details than that. There is certainly further work needed here. I think the first 3 points are sort of intuitive. And also the last point, I mean, we definitely need, on any of these components, further improvements will lead to a further speed up of this type of application of AI or digital techniques for that matter. Last part I want to cover is monitoring. Just to set the scene for that. So I think as most, I'm not sure exactly if the mix in the audience between like digital experts or AI experts and CCS experts, but at least for people who don't know this, MMV, so measurement, monitoring and verification is a crucial part of CO2 storage site development, because you need to prove that once you are injecting your CO2, and you see a schematic, that it's going to stay contained in your storage reservoir and not leak to other layers or even to surface. There's a wide regulatory framework around that. Often involves a risk analysis, typically bow tie. What you need to do is to ensure via your monitoring that you have containment of CO2 so that it doesn't leak, and link to that also conformance, that within your reservoir it behaves as expected. Now, if you throw every monitoring technique you potentially could have at this, it becomes so expensive that your CO2 project is not economically defendable anymore. So to improve that, there's many things. One of them is actually better hardware, like typically, for example, fiber optics in your wells, for example, where you cement in a fiber behind your casing and get a lot of data out of that. And I'll have examples on that in the next slide. And that immediately feeds into AI approach, because the amount of data coming out of these techniques is large, because you get so, like even with DAS, which then the acoustic signal, you get a signal every 0.5 microseconds. And then also for the entire length of the fiber. So AI can play a very big role in this, in reviewing that data automatically and integrating in automated systems where you only get like an alarm if something is behaving different than expected. And up to now, a lot of that is still manual task. Here's just last two slides of this. There's two examples here. This is for where you apply the fiber for DTS, which is distributed temperature sensing. And this is actually an example from operational side. So this is the Quest site, so Shell Quest site in Canada. What you see here is in the bottom graph for this 1 year. So as a function of time, this is just the injection. And sometimes you have a shut-in where nothing is injected, either planned, but sometimes unplanned. And this is the DTS signal, so also as a function of time, but now also as a function of depth, color coding the temperature measured using this fiber technique, where the cooler colors are during injection, when you're cooling down the formation, and then during shut-ins, the formation warms back up. And you get a lot of information out of that data. And here you see curves of the warm back. But currently, to analyze that is a lot of manual work, where we compare, for example, this warm back against semi-analytical physical models. And here we have a prototype tool where we train the tool with that DTS data, but also in the training combine it with other in-field measurements, namely the gauge data of because we also have physical gauges in the well that measure pressure and temperature at the storage formation, but also at surface. So we train it with both. But then when we once trained in the forward prediction, we only use the in-well field measurements and then compare the predicted temperature signal against the measured DTS signal and use that as a basis to screen for outliers. So here's an example of red predictions, blue actual for a shut-in period, here for an injection period. And then on top of that, there's well-defined metrics to calculate discrepancy, if it is significant or not. So you have a threshold and you have your metric. And if it's above the threshold, that would trigger an alarm to somebody in the operational team who can then review the data more carefully. And this would be a case where the prediction is outside of range, but in this case for a known reason, because we know this is a case where the well comes back on stream again. And we know, I won't go into the details, but the tool is not reliable under those conditions. But this is a case where it is injecting already again for a couple of days, and we have complete consistency. No alarm would be generated. In view of time, I will keep this one very short, but this is a similar application to DAS. So this is acoustic sensing, where the amount of data is extremely large, because here you get a data point everywhere along the fiber. Here the fiber can actually be vertical in a well, but there's also you can also use it for like telecom fibers or something, where you look at just seabed cables or something. In either case, you can get very high spatial resolution of, in this case, I think it's about a meter, and you get a time frequency that is very, very high, so 0.5 microseconds. Here it's really essential before we can start using this that we have an automation route for this. So this means that at the moment this is not used that much. We rely more on geophones. Sorry, couldn't get in the word. So geophones to measure this, but we want to move to the fiber approach. with that, I'll just close out. So I think I'm at time. So I'm happy to answer any questions if there's any time left for that.
Yes, I think we because we had the one cancellation, which makes the break a bit longer. I think we still have 1 or 2 minutes to answer some questions. So thank you very much, Jeroen. So we have some question in the chat, and one question is that if you, for instance, train the AI with 20,000 samples, and then you've done with your training, and in the meantime you have accrued another 10,000 samples or simulations, how easy is it to add those new samples into the model?
Okay, I'm not the AI specialist in the team, but I think to retrain a model takes a day or a couple of days, if I remember it well. But the intention is that we don't retrain, so we just want to do the training once, or maybe we come back to it after a year or something, but we don't want to retrain frequently. We just want to have a tool that's good enough in a statistical sense, given the observed uncertainty, compared to if we would use direct numerical simulation. And we believe we have that within the restrictions of the tool. That's just like this shoebox model, etc. Yeah.
Yep. Then another question is if your surrogates can generate brackets or probability distributions for injectivity and capacity. And the motivation behind the question is whether this could help assess risk at the strategic planning level.
Yeah, so the current tool is very much targeted at plume migration. It does predict pressure. So if you talk about storage capacity, it's often pressure constrained, usually. Sometimes it's plume constrained because maybe you don't want the plume to hit a certain fault or something. We are working on a version of the tool that's more targeted towards pressures. But in either case, yeah, but it can generate indeed probability distributions, etc., on any metrics that you would like to see. Yeah.
And then one last quick question: are your AI models availability to the public or the regulatory community for review and oversight?
No, this is a shell-only tool, but it is using technology that is publicly available. So we use like the NVIDIA modulus framework, for example. Like I said, it's similar to like the CCSNet tool that is publicly available. Yeah, for this we believe there is some IP in the way we trained it, etc. So we not directly sharing it, but there it does raise the question, and it was raised before with tools like this. Will it be accepted by the regulator, for example, if you use tools like this instead of direct numerical simulation? And that still is to be further tested, I think, if once we are at stage of applying this. But I think the answer to that is that, yeah, we can always run a simulation if a specific prediction is important, or a specific set of predictions is important. We can always use the model, this FNO, to generate those predictions, but then do some spot checks, for example, against direct numerical simulation. But I think it's an important topic. Yeah.
Thank you, Jeroen. There's still another question in the chat, so if you don't mind hanging around and maybe replying to some of them in more detail, if you like, that would be great. We will then move on to the next speaker, who is Aliyu from Argonne National Lab. And Aliyu will tell us something about generative AI and high-performance computing for the accelerated discovery of materials.
Yeah, hello. It is morning here in Chicago. So hello to everyone, wherever you are in the world. And okay, let me just dive into this topic. This is a project at Argonne National Lab that brings together colleagues across the Chicagoland area. And I want to share this idea with you with the expectation that some of you will be interested in one or many of the different ideas that we are combining together in this project. And if there is something for you, something that you are trying to explore, or something that you have expertise on, please feel free to let me know. And I'm sure that we can try to work together on one of these topics. So the main idea here is that for many decades, a lot of different stakeholders have been interested in the development of new materials for energy storage and conversion. And this includes, for example, carbon management, methane management, now hydrogen storage. Some of the challenges is that the discovery of these materials is no easy task. Those who are experimentalists know that it takes a lot of thought, of preparation, and costly materials to go and validate whether some specific materials are appropriate for one of these applications. The reason for this is that the chemical design space is vast, and only a few combinations of these materials really leads to optimal applications. And so the challenges that we are facing here are experiments. If they are not autonomous, if they do not involve robots, then they are time consuming. You cannot run tests 24/7, and that slows down your progress. If you are only a computational chemist and you are using even the new exascale supercomputers, some of these simulations are still slow, and they do not give you any initial guidance about where to go and poke in the chemical design space. So something else is needed. And the first thing that we say that is needed is that you need to bring a team that is capable of interacting with each other and with expertise in multiple domains. Here you see a combination of grad students with postdocs and staff and computational chemists. And the idea is that by combining this diverse set of perspectives on the problem, we can come up with something new. And this is what we have done. So here the name of the game, what we propose, the potential solution, is that we want to combine the best that we have in computational chemistry so that those who are hesitant, for example, of using AI, at least have some initial trust on the type of software that we are using to study these materials. For example, LAMMPS for molecular dynamics, or CP2K or PWDFT for density functional theory, and RASPA or GRASPA for grand canonical Monte Carlo simulations. And then what we do is we add a flavor of AI and experimental chemistry. And then we start tinkering about the output of this workflow and extract a few of these predicted materials. We're going to focus on metal organic frameworks and then try to see whether this approach leads to something that can be synthesized in a wet lab. So you can see this is the workflow. We use generative AI to build the building blocks of these materials. We take into account what is in the literature in the open world about computational, about experimental chemistry. We have designed code to assemble the ligands and the metal nodes of these materials autonomously, and then we start filtering these predictions. Traditional high throughput screening, very detailed molecular dynamic simulations, quantum chemistry, etc. And then once we find the best material, we do the techno-economic analysis to see whether it is worthwhile investing your money into this material. And then we share this information with people who know how to scale the synthesis of these materials. Let me say this, I think it is valuable for everyone who's not knowledgeable about what Argonne National Lab is doing. We have unique facilities in the planet. For example, in high performance computing, we have one of the few exascale supercomputers in the US. This is Aurora. And we also have other petascale supercomputers like Polaris. At Argonne, this leadership computing facility also provides AI accelerator chips like Sambanova or Cerebras if you want to accelerate discovery workflows with innovative hardware. And then we also have, on the experimental side of things, people who have decades of experience synthesizing materials. Now, diving into autonomous labs to accelerate the discovery. And finally, we have one of the brightest photon sources in the planet. So if you want to characterize these new materials, this is a unique facility where you can do this. And the beauty is that all of these facilities and the talent to maximize their use are under one roof. So this is one of the benefits you can get by interacting with us. And Argonne now has a carbon management initiative where what we're trying to do is to identify materials and technologies that are worthwhile investing in because they are not so expensive, so that we can explore how the carbon that is captured can be separated and converted into something valuable. So if you're in this domain, please feel free to contact me. And so let me now tell you a story about how my particular interest on this topic began. And this is through one of the Department of Energy projects that is called HPC for Energy Innovations. And I had the opportunity to interact with Total Energies. They wanted to deploy their software stacks in supercomputers at Argonne and to partner with us to start using generative AI to discover new metal organic frameworks. And so working with them, we designed a few independent modules that can talk to each other to discover new MOVs. And so the idea is that we designed a generative AI model that learned the chemistry, broadly speaking, from data sets like Geom. And then we also use MOVs data sets, like, for example, HMOV. We fragmented these materials, and then we used all these components to train a model capable of predicting new ligands or linkers. And then we decided on a few metal nodes that we were interested in and designed a custom code to assemble these materials so that the chemistry and the geometry would make sense. After that, we did some rigorous screening and testing using experimental data sets to make sure that the distance between any pair of atoms were consistent with experimental knowledge. And then we used a variety of computational chemistry software stacks to validate these new materials. And at the end of the day, we were able to identify a set of completely new metal organic frameworks with little computational resources. And I think this was the value proposition. If we have an AI model that understands chemistry, broadly speaking, and we develop the code to validate some of these structures, then we can accelerate the discovery of completely new materials that have high capacity for CO2 capture. And so this made some noise in different communities. In 2023, in the supercomputing meeting, which is the largest and most prestigious meeting for HPC applications, this work was recognized by the community of HPC and AI practitioners. And we got this paper in a really nice journal that amplified the impact of this work. Given the response of the community to this, we decided that it was time to go and do this at scale. And what does that mean? Well, that means that instead of using just Polaris, which is a petascale supercomputer with about 2,000 GPUs, we now want to go and do this in the new exascale supercomputers. And those are Aurora and Frontier. At the moment, we have been able to optimize this workflow that we call MOFA in Polaris that has NVIDIA GPUs and in Aurora that has Intel GPUs. And work is ongoing on Frontier, which is a supercomputer, exascale supercomputer at Oak Ridge National Lab. For this, I got one of these Inside Awards that provides you not only with access to these Aurora and Frontier computers, but also with staff support from these leadership class centers to optimize your code, which is incredible, the expertise that they provide. And then the idea is that in the Department of Energy, there are a few initiatives moving at a really high speed. And so we want to connect expertise and resources with this unique talent. And so from autonomous discovery, energy storage and conversion, and AI for science, energy, and security, we have created a team that brings hands-on expertise on these applications. And so let me now dive deeply into the type of workflow that we have created to discover these new materials. And this is what we call MOFA. And you can see this paper, it is in archive, so anybody can read it. So everything begins here. We go and select metal organic frameworks datasets, and datasets like Geom or Compass, where you have access to molecules that provide a good insight of chemistry, broadly speaking. The generative AI model that we are using is DeepLinker, which, as the name says, it is going to generate novel linkers. Now, these ligands may not be what you're looking for. And so, first of all, you need to process them. You need to filter them out and just keep those that are useful for your analysis. So that means ligands that are rigid and that are chemically diverse. All right. So once you produce these linkers or ligands, you hold them in queue in a supercomputer. And then once you have resources available, we use custom code to combine these ligands with metal nodes. And so you start assembling these as Lego blocks in a predefined geometry, PCU or whichever you have in mind. Now we have here an army of MOFs, and we are going to start validating the structure, looking at the separation between any pair of atoms, looking at the bonds or at the angles between the different bonds, whether the chemistry makes sense. Those that pass this basic test are now put in a priority queue. And as soon as resources are available, that means GPUs or CPUs, we start optimizing the cells of these materials with density functional theory. And here in the validation structure, let me also say that we do this using LAMPs for molecular dynamics. So we run the structure for several steps, and when we validate that the structure is stable, then we select it and put it in the priority queue. Once we optimize cells and get a detailed quantification of the partial charge landscape, then we use that information to now use grand canonical Monte Carlo simulation to estimate the absorption of CO2 or methane or whatever we want to study. And here we now look at the different materials that passed through all of these filtering and look at the properties of the ligands, the geometry, etc., and put that information back in a database and retrain the generative model. And we let this workflow run in an online learning loop for several hours. And what happens when we do this? Well, eventually, what we see is that the generative AI model is pushed in the right direction to start producing more stable MOFs and more capable MOFs. If we consider a figure of merit like capturing CO2 or methane. Now, let me give you a few more details about how the generative AI component works. So the initial part has to do with creating the fragments. And so we do this, as I said before, by looking at datasets like Compass, Geom, ArcMOF, HMOF, etc. So you have created the fragments, the molecular fragments make sense, that is really important. Then we use a graph neural network to look at some specific properties of these fragments. And then we start sampling these different fragments with a different number of atoms. And then we start the generative process. Basically, you add and remove noise. And here you can see what exactly is happening. You have these different structures, and now the model is going to predict what atoms and what type of connections they are going to have to create a structure that makes sense, chemically speaking. And obviously here you look at the bonds, the angles, etc. And finally, you end up with a structure that makes sense, okay? And here you can see how this process is happening. You produce these building blocks, you have some metal nodes, and then you assemble them into a predefined structure or geometry. Right, so those are the basic elements. When I was telling you about the validation of these materials, so we have a database, which is the OChemDB, where you can go and study the bond distances between different atoms. And so we have incorporated this into the workflow, and we do the analysis of the structures at a scale. This is a process that takes only a fraction of a second for each of the new MOVs that we are designing. And here is a movie that shows you, once you have assembled an entire MOV, we look at changes in the density, in the strain of the material, and those that have a small change, that means that once you run molecular dynamic simulations, the strain only changes a little bit, that means that they are going to be stable. However, those that have massive changes in density, as you can see on this movie, they collapse and we just filter them out. Then when we are computing the partial charges, here is where we use density functional theory, and we use all these different components of software stacks to do this analysis. And for the specific analysis of partial charges, we use charge model. With all this information in hand, now we can go and run Monte Carlo. And for that, we use RASPA2, which, as you may know, it only runs on CPUs. And the assumption that we make is that the MOV is going to be rigid. Bear in mind, some MOVs are not entirely rigid. Some of them are flexible, especially those used in drug design and discovery, and some others that recently have been used for CO2 capture. For these flexible MOVs, the analysis has to be more detailed. You need to find the large pore configuration of this material, and then you need to study the isotherms for the gas that you want to capture, whether it is CO2 or methane, and then you need to gradually follow the evolution of the material using DFT, and then once you have characterized the material properly, then you can use GRASPA or RASPA to quantify how good the material is for energy storage and conversion. Some results that we have obtained with this workflow in Polaris, you can see here that the performance of all these different components of the workflow run optimally, even a little better than linearly, which is great. And the money plot that you can see here is when we run the workflow on 450 nodes, and each node has 4 NVIDIA GPUs, you can see that as we scale the workflow to more and more nodes and more time, the workflow is performing better than linear. This means that we're not only scaling up and efficiently using all these computational resources, this also means that the quality of the MOVs that we are producing go beyond the amount of resources that we use. In other words, the properties of these MOVs are improving over time. We are filtering out less and less bad MOVs because we are getting higher quality materials. And this is really good. The other aspect that we studied had to do with the diversity of these linkers, the building blocks. And as you can see here, when we start the analysis, we have these squares and circles that are a bit transparent, and as time goes by, they get darker and darker. Well, we use linkers from the HMOV dataset for training. And you can see that as time goes by, the MOFA-generated linkers for these MOVs are occupying different areas of the parameter space, which means that over time we are creating better and chemically diverse linkers, which is great. The other figure of merit is the strain, which characterizes the stability of the MOVs. And you can see that when we start the simulation, well, they are not that great, right? And they are similar to the data set that we use for training of the generative model, which is HMOV. But as time goes by, you see that these squares get darker and darker. That means more runtime, and the strain gets better and better. And again, this is confirmation that the workflow is producing better and better MOFs over time. Now, one of the really nice things that we got out of running this workflow in Polaris is that when we use this amount of GPUs for about 3 hours, we were able to obtain really competitive MOFs in terms of CO2 capture, as you can see here. This is in the top 10 of metal organic frameworks in the HMOF dataset. Note that I said top 10, not top 10%. In only 3 hours, we were able to produce one of the best MOFs that you're going to find in that dataset that is completely new. The components that you see here, the ligands, etc., these are not available in that dataset. This is all new. Now, let me transition to MOFA version 2, which is now being deployed, which is now completely deployed in Aurora. And we have been able to run it in over 12,000 GPUs. One of the new components that we have is that in the optimization of cells, we are now using PWDFT, which has been designed to run at exascale, and this is now replacing CP2K. And for the computation of the CO2 capacity, we are using GRASPA. And the reason for this is that GRASPA runs on GPUs, and Aurora has over 60,000 GPUs. So we want to use those resources efficiently. And so the main idea is the same. The workflow now is better optimized to run on Intel GPUs. And one of the very nice things about using GRASPA is that in the past, we were only characterizing MOFs without any stuff around them. No water, no additional gases to CO2. It was a very ideal situation, but when we want to use these materials, well, typically these are surrounded by a multitude of gases. They are surrounded by moist or water, and this is what industry really wants to see. What is going to be the performance of these materials in realistic conditions? And well, with GRASPA, now we can run the simulations. And as you can see here, it is just a matter of minutes to characterize one of these MOFs, for example, for hydrogen storage or for CO2 capture. Consider that with traditional RASPA simulations that run on CPUs, this could take days, if not up to a week. And so, since the workflow is going to complete one of these full cycles in a matter of maybe 1 hour, it is of paramount importance that these calculations finish in a reasonable amount of time. And finishing in minutes is a game changer. Even beyond the basic capabilities of GRASPA, we have been using this NVIDIA capability, MPS, so that we can parallelize the GRASPA computations and we can get more throughput, as you can see here. So all of these are really good news. In plain words, this means that we can now study MOFs in realistic conditions in a reasonable amount of time. So we're reducing time to discovery. And what you can also see here is that for the type of materials that are of great relevance to the Department of Energy in the US, and I assume to energy companies around the planet, we can go and characterize some of the best MOF data sets like core MOF very rapidly. So if you are already in the business of creating MOFs and you want to understand how good they are in realistic conditions, we have the tools to do that with you. So at this moment, this workflow that I have described to you provides the insights from experimental chemistry, from computational chemistry, the best methods that we have in generative AI, and exascale supercomputers, where this workflow is running at a scale. It is ready to be applied not only for CO2 capture, but also for methane capture, for hydrogen storage. We can tailor the capabilities of this workflow based on what you want to study. And a selling point for us at Argonne is that this is running in Aurora. That provides unique capabilities for this type of really complex workflows. So what do we try to get out of this in collaboration with some of you? Well, one of the key aspects around the planet right now has to do with energy independence. How can we go and use materials to enable this? It's a big open question. And if we happen to discover some of these materials, is it the case that we can find only a handful of these? Or we should go and try to do something like this, where we go beyond what we understand in chemistry right now, and we get some help from AI to go and find a larger set of materials that are cost-wise what we prefer to use, because that means that we can create them at a scale. And obviously, in the long term, what we want to do is to attain economic prosperity. And so for industry, this is what we are offering, to help you find materials that are useful for your applications. And we have, as you saw, not only the expertise, but the facilities to do that. And for the Department of Energy that has a global view of these challenges, we really are interested in the creation of new materials so that we can attain a circular economy. So how can you integrate your expertise or your work with what we are doing? So if you are knowledgeable of synthesis of materials, and there is where we're putting some extra effort right now, creating this menu of synthesized materials. If you have any insights about something that is really hot right now and promising, please talk to us. In the medium term, the idea is going to be to not only produce a gram, of these new MOVs or COVs or HOVs just to play with them. We are going to be scaling this up to kilogram and then to the range where this is now attractive to industry. But we want to get there together. And then in the long term, our plan is to continue advancing AI applications, not only using what other people are developing, but to actually continue advancing AI applications. I use the work that we are doing at Argonne on autonomous discovery labs, leveraging robots to do these experiments 24/7 and to connect these experiments with our supercomputers. And as quantum and Z-scale computing appear on the horizon, be ready to harness these developments. So this is what we offer to you. If you're interested, if you have questions about this, then hopefully we can work together. And if you want to take a screenshot of my information, feel free to do it, and then we can have a conversation. Let me thank my sponsors for this work. Thank you.
Thank you very much for the very in-depth presentation on how exactly you analyze the MOVs. And we have a question in the chat, and it is how much degradation in adsorption is caused by water in the feed, and how well can you predict the MOF life and the number of cycles?
So one of the, if you talk to oil and gas companies, this is one of the first questions that they ask you. How performant is the material in the presence of water? Because we do know that a large number of MOFs that look beautiful, out of a supercomputer and quite performant, once you add a little bit of moist, that significantly degrades their capability, their durability, etc. So it is one of the, I would say, one of the top questions that you get out of industry partners. How good is the MOF in the presence of water, and how selective it is in the presence of a mixture of gases? So if there is not only CO2, but there is nitrogen, methane, or any other gas surrounding this material, how selective this is going to be capturing the gas that I am interested in, and how good this is going to be to store this material for a given amount of time. So, this is one of the key concerns on the real application of these materials. So that is for water. What was the other question, Jasmin?
How well can you predict the MOF life and the number of cycles before it degrades? So
for that, we use lamps, and I think we have a really good understanding of that. But I would say that in addition to testing how many cycles this can perform. For example, if it is breathing, how many times you can do that. I think the main simulation that is going to provide insights on how useful the material is, again, is GCMC, these Monte Carlo simulations, where you now surround the material with gases or water, and there you can study the performance of the material. And as I was telling you before, some of those studies take days, if not weeks, because the analysis is very detailed. But with GRASPA now, we can complete that analysis in just a few minutes. So it is going to depend on the material that you have in mind, whether it is a rigid MOF or a flexible MOF. But if you have something in mind, then we can run the simulation and give you a good answer, a quantitative answer.
Yeah, thank you. We have to move on, but I think there is another question in the chat. So if you don't mind hanging around and maybe responding to that in more detail, if you can, that would be great. And now our next speaker is Athos Nathanael from the Colorado School of Mines. And Athos will be talking about transforming subsurface analysis with advanced AI and machine learning techniques.
Hi, everyone. Good morning from Colorado, United States. My name is Athos Nathanael, and I'm a postdoctoral researcher at the Colorado School of Mines. First, I want to start by thanking IEAGHG for giving me the opportunity to present to all of you here today, and all the sponsors that made this project feasible. So in the next 18 minutes or so, I'll share how artificial intelligence and machine learning are transforming conventional subsurface analysis and also revolutionizing the understanding of the subsurface. I'll focus on how different AI and machine learning applications and models can utilize data across various scales and ultimately assist us in mineral, hydrocarbon exploration, and of course, the focus of this workshop, CCUS. I'll then give a brief overview of how my research during my PhD and postdoc leverage multiple aspects of machine learning and AI, from computer vision to natural language processing for interpreting geological data, and concluded with generative AI techniques for better seismic imaging. Before diving into details, let me just give you a brief roadmap of this presentation. First, I'll set the stage with the motivation. Why do we care about understanding the subsurface in the first place? And a key concept I'm going to cover here is subsurface geology and depositional environments. Next, I'll introduce how AI and machine learning bring new geoscience capabilities. We know that traditional methods face challenges with the sheer volume and complexity of all the data we have. And this is where AI actually offers some powerful solutions. Then I'll highlight two main threads of my research. And as I just mentioned, my PhD work involved these aspects of AI and machine learning to interpret the depositional environment while quantifying the uncertainty. And then how can I use generative AI for seismic imaging. And I'll conclude with a few key takeaways and how AI actually transforms our understanding the subsurface. So let's start with just a very basic definition for the non-geologists. What is a depositional environment? Very briefly, just a setting or location in which sediments are deposited and eventually become a sedimentary rock of some type. You can think of environments like a river channel or a lake, a beach, or a deep ocean. Now, each of these settings was formed in different conditions, and each environment leaves a distinct signature in the sediment. That signature can be different sedimentary structures, different grain sizes, fossils, and other things. Now, geologists study these characteristics to deduce which depositional environment a rock unit came from. And this is actually understanding that the environment is the backbone of interpreting the sedimentary rocks and thus understanding what's underlying under the ground, the subsurface. And this is crucial because it's going to tell us about the geologic history of an area and what we might expect in terms of rock properties or mineral content. Now, let's see why this actually matters so much in practical applications. So in basic geology and paleoclimate studies, by understanding the environment, geoscientists can reconstruct what Earth's past looked like. Then many mineral deposits are tied to very specific environments, and thus knowing the depositional setting of a rock formation, we can hint what mineral resources might contain or where we can explore next. Then we have hydrocarbon exploration is one of the areas actually where understanding the geology is absolutely critical. And the depositional setting controls the architecture and heterogeneity of the reservoirs. If we make a mistake in interpretation, we might overestimate or underestimate hydrocarbon quantity or how easily it can flow through the reservoir and produce it. Now, in terms of CCS, when we inject the CO2 in the subsurface, let's say into saline formation or a depleted oil field, we need a reservoir with sufficient pore space and a good seal on top to trap the CO2. And the depositional environment influences pore size, connectivity, and how actually the CO2 plume will move and be trapped. And ultimately, it helps us in decision making and assessing storage capacity and security. Now, the common thread across all these different domains is getting the depositional environment interpretation correct, and this is going to lead us to better site characterization and decision making. However, doing this interpretation is not always a straightforward process. And this is because we have different data types across various scales that can provide important pieces of information when combined together. And this gives us a more complete, holistic view of the subsurface. Now, very briefly, these data types include seismic data, which essentially captures how acoustic waves propagate through the subsurface to map large-scale rock properties, identify stratigraphic layer geometries, and delineate structural features. Then we have outcrop data, providing the ground truth observations of sedimentary facies and relationships between stratigraphic elements from exposed rock facies to inform depositional interpretations. Then we have the well log data, which records continuously in the borehole measurements, either that's in terms of rock lithology or petrophysical properties such as porosity, density, resistivity. And this gives us a lot of details about the vertical profiling. Then we have the core data, which deliver high resolution sedimentological descriptions, stratigraphic context, and measure physical properties from discrete rock samples extracted from the subsurface. And finally, we have the microcity images, which capture the micron scale visualizations of the pore networks, mineral faces, and related petrophysical properties within the rock samples. So here what you can see is a very high level overview of the different data types across spanning from the micron scale up to thousands of kilometers, which are the seismic data. And combining all these different types of geological data gives us the understanding, a holistic understanding of the subsurface. And with that, we'll go to the challenges in the traditional subsurface analysis. Interpreting the subsurface has always been challenging, even before the age of big data. And if we look at more specific examples, the first one I'll mention is just the data. And nowadays we have tons of data about the subsurface. You can imagine for a single CCUS or oil and gas well, we have thousands of feet of core, well logs, or if there's 3D seismic survey, we have huge span of data with tens of square kilometers with millions of data points. So humans are very good at focusing on one piece at a time, but integrating all these pieces across the different scales is actually very challenging. And this leads us to the next problem, which is geology is a multi-scale problem because we have, as I mentioned, data across different scales, and occasionally features we see in one scale are not visible on a different one. And bridging these scales is actually very challenging. Now, traditionally, making sense of all this data is done by expert geologists, geophysicists, etc. And as an example, sedimentologists might spend weeks examining cores or outcrops or thin sections to interpret the depositional phases. It requires a lot of training, and understanding the subtle sedimentary structures and geological signals comes from experience. Saying that, this process is also subjective, meaning that two or more experts might draw slightly different conclusions from the same piece of data. And lastly, human bias and prior experience influence these interpretations, leading us to the uncertainty the geological data is inherent to, especially when our data is noisy or incomplete. Multiple interpretations are possible, and quantifying this uncertainty is also difficult with manual methods. Lastly, we have the siloed data, which is another challenge as we have many different kinds of data. So for example, you can have text reports, images, numerical sensor data, or grids. And these often live in separate software or with different specialists. One person might be reading reports, another might be looking at seismic. Integrating this information manually in a cohesive way is actually very, very hard. So all these factors mean that traditional subsurface analysis can be slow, expensive, and uncertain. And this is where we see huge potential for AI and machine learning to help. AI excels at finding patterns in large complex data sets, and this is exactly the kind of challenge we have in the subsurface interpretation. Next, I'll talk about how AI modern techniques can address some of these issues, augmenting human experts rather than actually replacing them, to improve both speed and accuracy of the analysis. So over the past decade, AI has made incredible steps, especially in the advent of deep learning, with these algorithms excelling at vision, such as image analysis, language tasks, and can detect patterns and relationships to the data. That might be very difficult for human to discern, especially when the data volume is vast or the patterns are subtle and there are multivariate correlations between them. So a few common tasks I show here, and Julio in the beginning gave a very nice overview, cover computer vision, natural language processing, and generative and large language models. So crucially, what I want to mention here is that AI does not and should not replace human experts. Instead, it augments our work. And the best outcome is when we have a synergy, the AI handling the heavy data crunching and find initial patterns, and then we have geoscientists or experts in any domain providing oversight, validation, and domain knowledge to ensure interpretations make sense in the real world. So we have talked about geological carbon storage, CCUS, and AI comes in essentially to enhance the efficiency and effectiveness of all these processes by integrating different amounts and types of data, building predictive models, and monitor in real time. So a few of the common applications, you can see them here, spanning from site characterization, monitoring surveillance, risk assessment and management, data-driven insights, training and education, which is an important one, and then lastly, permitting. So in this presentation, I'll focus on site characterization and briefly touch a few of the other points. Now, during my PhD, I focused on the problem of interpreting depositional environments using AI. And what I did, I built a model ensemble utilizing various AI methods to essentially do some of what a sedimentologist or a stratigrapher would do. And the goal was to do it faster while quantifying the uncertainty, and also find a way to transfer knowledge and observations from one scale to another. So the data used include outcrop images, which was my main type of data. Then we had textual information, well reports, geological descriptions. And finally, we had some quantitative information, well logs, stratigraphic data to provide us with some physical measurements. The techniques I employed starts with computer vision, where I trained different models to recognize and segment sedimentary facies from the outcrop images. Then I used natural language processing to parse and extract key descriptors from text to inform my interpretation. And then I combined both of these different types of information using neural networks to come up to a conclusion and interpret the environment while also I quantify the uncertainty. Now I'll show you a few results of the computer vision first. So on static images, I used image classification to classify different fossil types across my images, object detection for detecting various sedimentary structures, and finally, segmentation to actually delineate in pixel level detail my different sedimentary structures, but also lithology types. And here you see a very brief application of the same model, but was actually trained purely on 2D images, but it was actually tested in this case in a 3D outcrop video. And as you can see, it can still work and make some predictions in real time, although it has never seen 3D data or any sort of real-time data. Now, as I mentioned before, one of my goals was to transfer the knowledge from one scale to the other. So I trained my model, again, is the same exact model, trained only with outcrop images. But when I tested on core video, you can see that it's still able to make predictions, although it has never seen a core image in its training, which is very interesting and very promising for adaptation on different scales. And another example to put in CCUS context, what you see on the left is a simulation of a tank experiment, essentially. It's called the Fluid Flower Project. And what you see here is the CO2 plume and how it migrates through the formations. And the goal here was just to track it or monitor its movement across the formations. Now, the second element was the natural language processing, and essentially what I want to achieve here was to incorporate domain knowledge and expertise in my interpretations and inform my interpretations. So the computer vision gives us a list of labels, if you like, and by harnessing the power of NLP, I took these individual elements or labels and combined them into more meaningful interpretations. So the idea was to mine literature for different interpretations. And I started by taking, for an example here, this is from a paper. I put it through my NLP pipeline, and I cleaned the text, and I kept only terms that are meaningful or useful for the interpretation of the positional environment. Now, taking all these, I used neural networks or convolutional neural network in this case to make meaningful combinations of these sequences. So essentially, the different labels were my inputs, and then the output was different interpretations of the positional environment or facies associations. So the outcome of my PhD was a system that outputs a list of predicted depositional environments or facies with a confidence level. And imagine you have this image of an outcrop, and you feed to the model. What's going to do, it's going to run through the different computer vision elements, and it's going to extract using OCR whatever we observe in the image. And I put everything in the user interface for the sole purpose of having a geologist evaluate these inputs over here and obviously my outputs. So these are editable. You can remove or add anything you like. And once you update the model, you get a list of potential interpretations. Let me zoom in here. With the probability assigned for each prediction individually. So the whole idea is what I mentioned previously, the bias and the multiple possible interpretations from a single piece of data coming from different people. And the idea is to get an extensive list, if possible, of many different interpretations with different probabilities, because occasionally this might gives us new insights about an interpretation of a specific area. So in this particular example, you see we have prediction probability of 100%, and the second one on the list is about 55% certain, and the third one is very low, and everything else is 0. But there are occasions that we have these probabilities being very close to each other, and it might be worthwhile spending some time evaluating each scenario and its feasibility. Now, the next shift in gears, I'll talk about generative AI for seismic imaging. The main challenge we have in seismic is that seismic surveys sometimes have gaps or limitations in the data, especially if we have older data. So if seismic was shot back in the 70s, we have low resolution than what we have today. So we want to cover noisy data, sparse coverage, and also limit the resolution. And all these can leave us with an incomplete picture of the subsurface. Oh, and of course, money. It's very expensive to shoot a new seismic survey whenever we don't have data or we're missing data. So the motivation behind this, how can I leverage generative AI to either generate new data or enhance and improve all data we already have. So the idea was to use stable diffusion methods that learn from existing high-quality seismic data and generate enhanced images that look like, obviously, like our training data, but also augment existing data by improving resolution. And taking this data, we can use them, for example, in additional machine learning workflows and models to perform different tasks. The workflow I have here is very simple in theory, definitely not simple in practice. I start with data set and pre-processing. So imagine you have your SGY file from, let's say, any field. What I show here is from a synthetic data set. So we have our cube, and what I do, I slice it in different time slices. So essentially building images of 2D amplitude maps. And I create this data set. Then I take this data set and I use it as my input to the stable diffusion model. And what the model does, it just generates new images based on the training data. So imagine you have a field that you want to explore, but you have a very specific location on the field that we don't have any data, right? So the idea is if we train it with data surrounding that location, can we kind of populate or fill this location with potential scenarios or test cases. And the last step was to upscale the synthetic data. This looks very complicated, and this is what translates to in simple terms. We start with our original image, and slowly from every step we introduce more noise until the image is not visible. Then we try to recover the initial image, and we go backwards. So to give you more context, we have the original image, introduce noise until nothing is visible, and then the model learns through both processes. And this is why it's very important to feed it with, to train it with high quality data that captures the different variances we want. So the result of the synthetic seismic I generated is just a few amplitude maps. As you can see, going from A to all the way to F, it gets more chaotic and more unrealistic. And all this comes down to the inference parameters you use during the testing stage. So it's a little of tweaking and experimenting with how the model performs and how it generates the images. It's much more complicated than that, but this is what it breaks down to in simple terms. And then upscaling seismic image amplitude maps, we have our, I'll say, bad quality in brackets data, low resolution, but it's not easy to interpret or understand what we see here. And running it through this image upscaler, we see that on the right we have a much more crisp image with more details that actually is more interpretable and useful to incorporate in the workflow. So the key takeaways is that the best solutions arise when geologists, engineers, and data scientists work together. AI models need geological insight to train the data, validate them, and add a physics context, which is very important. Then encoding domain knowledge into these models ensures the results make sense. And this can be via custom features, constraints, or training labels. The other one important element is the continuous feedback. So field data or expert feedback refine the AI predictions. So for example, if something is misclassified, in the example I showed previously, a geologist might say, this is the correct answer. And this can be fed in the model to improve it in real time, or what we can call active learning in this case. Then we have developing explainable AI is a key for trust, actually. Highlighting which features led to a particular interpretation is very important for us understanding how these models work. And that's why they call them black box models, because we don't know exactly how they come to a conclusion sometimes. And the most important thing, I think, is geoscientists learning from data scientists and AI specialists learning from geologists, and essentially to create a common language. And this skill set is important for the next generation tackling subsurface problems. So we have reinforced how critical is understanding the positional environments for any subsurface endeavor, and they are the key to predicting rock properties and behavior. And this hasn't changed. If anything, AI makes using this knowledge easier and more quantitative. Advanced AI and machine learning is not here to replace geologists, but actually amplify the work we do, transforming workflows by handling data overload, finding patterns we might miss, and offer rapid, repeatable analysis. The greatest gains from this integration is combining different types of data, so field geology, lab data, and geophysics with AI algorithms. Ultimately, the approaches discussed lead to more confident decision-making in exploration in CCUS. By quantifying uncertainty and continuously integrating new data, we reduce the risk of dry wells, CO2 leakage, and optimize resource extraction, and ensure, of course, safer storage. And lastly, as AI models become even more sophisticated, and as our datasets grow, we expect subsurface analysis to become increasingly predictive and reliable. And human expertise and AI synergy will be central to tackling future energy and environmental challenges. And with that, I want to thank all the sponsors for this research. Thank you.
Yes, thank you very much, Athos, for a very great presentation. We are running a bit short on time because I think I promised actually a larger break, but we are now back to the old break time. But the presentation and question were just so good that I didn't want to cut anything short. We have one short question for you. Someone is asking if you used an available software for training and validating your model, or whether you made your own code using Python or MATLAB or...
It was a combination of both. For certain elements, I fine-tuned certain models, for example, the stable diffusion, the generative AI, and parts of my PhD work were publicly available, but I also had to modify certain aspects to make them work the way I wanted them for interpreting the outcrops. And it was a lot of fine-tuning and changing important steps in the original workflows to make this happen.
Right. Thank you. Then now we have time for a short break. So we will reconvene here with the next presentation in about 10 minutes time.
Jasmin, are you hearing me? Am I next, or is there a Helen Smythe from Halliburton? I can't hear you. You're muted.
Yeah, sorry. Yeah, Helen is not with us today, unfortunately. So we were thinking of extending into the break, but then discussions went on so well. So yes, you would have the first presentation now after the break.
Okay, great. Thank you.
Right.
Good afternoon, everyone, and welcome back from the break. I hope you've all had a refreshing time. We're ready to kickstart the afternoon session, and our next speaker is Ken from GHG Underground. Hi, Ken, you're on.
Yes, thank you very much, Abdul'Aziz.
Fantastic. Yeah, very well. And Ken is going to speak to us on AI-informed risk assessment for CCS, CCUS. The floor is yours, Ken.
Thank you very much. Well, good afternoon, good morning, whatever time zone you're in. This talk is on AI-informed risk assessment for CCS and CCUS projects. I'm Ken Nadabanj-Talene, and my consultancy is called GHG Underground. I've been working in CCS risk assessment since 2007. The previous presentation from Athos I found very inspiring, and I'd particularly like to remark that AI at present can be used to augment human experts, because that's very much the thrust that my presentation will have. I will be speaking with you to some extent about expert workshops, expert elicitation workshops, and I can now see from Athos's presentation how AI actually might in the future be able to be applied to those in a more comprehensive way than I will describe today. Well, a few days ago, a colleague of mine decided to ask the AI engine ChatGPT how AI could help with CCS risk assessment. The slide shows an excerpt of what it responded. ChatGPT cannot access confidential data, cannot perform quantitative risk calculations by itself, and cannot make final risk judgments without human oversight. The first X notes unless you provide that context, which presents a real opportunity for AI that I'll describe later. For the second X, there are computational tools from the US National Risk Assessment Partnership. We just saw some that are used by Shell and Colorado School of Mines, and there are others. The last X is a main focus of this talk, and I will suggest how AI might be used to support human judgments. So that was last week. Just yesterday, I heard on the radio that Layla Isaac of Johns Hopkins University had investigated how well AI could interpret what humans were conveying visually and non-verbally in conversation. Dr. Isaac's results show that AI is not at all good at that. We convey more and different information in face-to-face settings than is present in words alone. How much does AI miss? Well, we're not going to debate the details here, but the answer is a lot. In order to see how AI might, I skipped forward a slide there. In order to see how AI might assist the risk assessment task, we first need to understand some basic elements of risk assessment itself. I'm going to step quickly through 4 elements that, once defined, make it possible to develop risk quantities or values that can be compared. Then I'll describe how those values have been generated by human experts, and finally I'll address potential AI contributions. First, the basic definitions. To evaluate and compare risks, we must define 4 things. First of all, we identify the entities that we care about that bear risk, that might be at risk, which can be called project values. Secondly, we identify the entities that bring risk to those project values, which go by various names, but we'll focus on scenarios. Third, what metrics can quantify scenario risk? Most contexts define risk as the product of impact severity, S, and likelihood, L. Both of these are semi-quantitative. Project values are the things that ultimately are defined by the project managers as being what they care about, the things to which they try to minimize risk. Here are some typical examples. Projects care about executing on time and within budget, obviously, but also care, so to speak, about not harming people or the environment, about adhering to regulations, and so forth. Each project value has effectively a goal that describes 0 negative impact, so the scale of impact severity is defined in relation to this no negative impact scale. Or sorry, no negative impact state. Scenarios are the what-ifs that bring risk to project values. Chains of events that, if they happen, will do some damage. Here are a few scenarios from a project that aimed at sub-seafloor CO2 injection. Well, if leakage to the seafloor did happen, how would we evaluate the severity of the damage that it would do? Here's a severity scale developed by a different project in consultation with that project's experts. You, as a project expert in this case, you might conclude that environmental damage from leakage would cause minor impact, so you would rate this category a 1. Yet leakage would also result in major negative media coverage, so that would make it a 3. Others would judge it differently, and that's why we need to incorporate multiple views from multiple experts. And just to hammer home the point, only people can decide the importance of any impact. Only people can develop these scales. Well, how likely would it be for leakage to happen? That's a little easier to scale, but it still depends on judgment. Virtually all projects use a 1 through 5 scale, but different projects have applied different words and numbers. AI might be able to help with the most quantitative version of that, but only if the engine can find enough data for scenarios that are similar enough to this one. Severity and likelihood are usually shown together on a matrix like this one. If each property is scaled 1 through 5, then the product risk becomes scaled from 1 through 25. Low risks plot in the upper left blue and high risks in the lower right dark red. Looking at the broad band of yellow intermediate risks, it matters a lot for treatment choices whether a scenario has high severity and low likelihood or the opposite. Well, how do we get these values of severity, likelihood, and risk? Well, with experts at hand, we first assemble, assimilate, and share project-relevant information. Then on that basis, we judge and assign S and L values and calculate risk. And then we determine how each risk, that is, each scenario, should be treated. And who are we? Well, we are the people who have various relevant ideas, relevant areas of technical expertise. People who know in detail about project plans and applicable regulations, and people who know the site well, subject matter experts, SMEs, and stakeholders. And every one of us has biases, another reason that we need multiple experts. If you haven't read Danny Kahneman's book, Thinking Fast and Slow, do. Well, experts have personal knowledge in various areas, of course, but here I want to point out that having a group of experts in a live workshop often elicits more information than anyone initially thought was available. And it also enables validating and testing information. AI can potentially supplement this information in particular ways. Well, I just got through saying that live discussion is important, so why the web? Well, we can use live workshops and the web. If you want to open a second browser window right now to the URL that's shown on the screen, you can see how easy this is to do. But do come back. Using a web app during the workshop or asynchronously before or after the workshop, experts can provide both S and L values for a given scenario by clicking once on the matrix. The values can be pairs of integers 1 through 5 or any decimals in between. So for example, when 20 experts evaluated this scenario, the scenario being seismic survey badly executed yields poor data, sorry, lost my place here. Here are their results. Each tadpole is one expert's vote. We'd call this a low to moderate risk, with the tadpoles plotting in the blue through yellow. In contrast, this scenario was judged to have a pretty, there it is. This This scenario was judged to have a pretty high risk. Altogether, the 64 scenarios for this project, you won't be able to read them here, were ranked by risk. The risk rankings and the S&L values themselves provide the essential information that informs the allocation of resources for risk treatment and control. Now that we've seen how risk is evaluated, how might AI contribute to that process? I'm going to finish up with a slide that makes certain assumptions or its assertions explicit, and lastly, another slide indicating where AI might help. These are definitely challengeable assertions here. It's something for discussion. So here are 3 assumptions and 1 conclusion. I guess you could call them all assertions. Anyway, they're statements that I think are true at the moment. First, geologic projects, and especially first-of-a-kind projects, always rely on sparse data. The data that you may have on similar projects or settings is never perfectly applicable to the current project. You have to interpret it. Second, only humans can weigh and judge humanly important values. And only humans, so far, have a chance of judging the importance of what they don't know. How big is that area of unknown unknowns, and what does it matter for risk? Third, subject matter experts and stakeholders are the best qualified to identify reliable information, to separate the wheat from the chaff. Garbage in, garbage out still applies in the age of AI. And those 3 assertions lead to my tentative conclusion that AI is best applied to inform the human experts who are the ones to make judgments about risk. So how can AI best aid CCS project risk assessment? The first point here is partly obvious. AI can provide access to vast data, but the real value may lie in curating the data used by an AI engine. Remove the chaff and highlight the wheat before unleashing AI upon it. The second point notes that an AI engine is not necessarily limited to publicly available information. Project operators themselves, and as advised by experts, may enable the AI engine to operate on confidential information, whether or not the risk assessment results will be made public. Third, a trained AI engine can provide fingertip, on-demand access to information to the experts who are evaluating risk. In other words, answers may be available when the question comes up. This is valuable both to experts doing individual evaluations and as a resource available during a workshop. And last, the application of AI might begin to make risk evaluations comparable across different projects. That remains to be seen. All the points on this slide and the previous one are offered for consideration and debate. I would say none of them are hard and fast, and certainly none of them are permanent. Well, that's what I have. If there's time left for questions, I'm sure there will be a few. Jasmin, by the way, or Abdul'Aziz, I do not have access to the chat window for some reason, so you'll need to speak any questions to me. Thank you.
Thanks, Ken. This is indeed very interesting content, very interesting presentation. Thank you for sharing this with us. Let me try to see if I can be able to pick out some questions from the chat. Not yet. Just a couple of questions from my end. Can you elaborate just a bit on how this AI-informed approach compares to traditional quantitative risk assessment methods in terms of accuracy or decision-making value?
Yes, I can make some comments on that. First of all, the truly quantitative aspects of what might broadly be called risk assessment, I would say come from various computational tools, such as we saw applied by Shell, Colorado School of Mines, the NRAP partnership, so on and so forth. What these two tools do is provide quantitative insights about very narrowly defined problems. They have nothing, well, almost nothing to do with what is more generally called the risk, which involves both the probability of some impact occurring and the severity, or you could say the meaning or the importance of that impact. So the truly quantitative tools really do not directly address what risk professionals call risk. When we use scales like 1 through 5 for severity and likelihood, those are at best semi-quantitative. There are ways to put some kind of scalable number onto a much more vague and really non-quantifiable concept so that we can compare things. Now, I would still say that in a traditional risk workshop where experts are providing these 1 through 5 values and ultimately 1 through 25 values for risk, that is still a semi-quantitative exercise. And if those same experts are further informed by access to AI tools and even well-curated, well-trained AI tools, the overall exercise of risk is still judgmental and semi-quantifiable.
Thanks for your response, Ken. Just a quick one, we have just a couple of minutes. Our keynote speaker earlier mentioned and discussed about the quality of data in training AI. From your point of view, from your perspective, what types of data inputs or sources are most valuable for training AI models in CCS risk assessment? And how do you address these potential data gaps?
I think that one of the most interesting opportunities for AI to contribute to risk assessment is through the application of large language models, which can be pointed at curated data sets and data sets that are curated by the experts who will be doing the risk assessment. So in other words, let's say you have a group of 20 or 30 experts who are ultimately going to be performing a risk assessment for a project, and by way of a workshop probably, those very experts are the same ones who can best identify literature that is most pertinent, most applicable to the project, and they can in effect through that method screen out all kinds of literature that an AI engine might find on the web that is really just going to add to noise. So I think the curation of the database that an AI engine will be focused on is a very important aspect. And then secondly, the potential access to vast amounts of confidential data is also a great opportunity.
Thanks, Ken. We're right on time. There is a couple of questions in the chat. If you do have the time and availability, your response will be appreciated within the tool of the chat. Thanks, Ken.
Thank you, Abdul'Aziz. I do not have access to the chat. If you could email those to me, I'll be happy to answer them.
Absolutely, I'll do that. Thank you very much. Right, so our next speaker is Phil Friedmann from Drax, as well as Simon Hasbach from Uppers Energy, and they will be speaking on the use of AI with respect to biomass origin and tracking. Phil, Simon.
Thanks, Abdullah. Hopefully the audio is coming through clear. So Simon and myself both work for Drax. It's a legacy thing that his email address suggests he works for a different business. Just to introduce ourselves very quickly. So I've worked for Drax for almost 10 years. My role is primarily around using automation and AI in conjunction together. And Simon is the data engineering manager at Drax. And so we're going to do a bit of a double act handing over, and we'll try our best to keep things moving along smoothly and field questions as we go along. So over to you, Si.
Thanks, Phil, and good afternoon, good morning to everyone. DRAX is about bioenergy, carbon capture and storage. We've talked a lot on the conference today about the carbon capture and storage, but what Phil and I have spent the last 12 months or so doing is looking at the bioenergy part of that equation. And in DRAX's case, bioenergy means low-grade woody fibre and residue fibre like sawdust that we then turn into biomass pellets and use to generate electricity. And within data and data science, we've been exploring ways to help our business teams ensure the sustainability of that biomass and the carbon sequestration potential of the managed forests from where that biomass occurs. We have lots of teams within DRAX that already do these jobs, but we found AI to be most helpful supporting them, particularly with supplier onboarding. So DRAX doesn't harvest biomass itself. We have suppliers, mainly in North America, and there is a very rigorous onboarding process for those suppliers. They need to send us lots of information, including the exact locations of their harvest areas. And our teams will go and meet with the suppliers and make sure that all of the sustainability criteria are met. And we found AI to be most helpful in helping to verify that information, both for new suppliers, but also due diligence on existing suppliers as well. And the big screenshot on this slide of a satellite looking down on the Earth is one of the key benefits that we're getting from the AI. It's the interpretation and analysis of satellite imagery from all across our supply base. Pause there. Phil, do you want to move on to the next slide?
Very good. Thank you. So moving on a little bit more in detail about exactly how we're using the AI to help with harvest location identification, specifically using satellite imagery, such as shown on the previous one for the Sentinel-2. We can use it to produce timely teenager. Apologies, doing his homework, so I can't argue. We can use it to produce image mosaics, which is layers of combined processed images from satellite imagery, which helps us in terms of being able to maintain radiometric and geometric fidelity to understand harvest locations and specific cutouts or small pieces of land that weren't relevant to those harvest locations from supplier data. This, from a processing point of view, allows us to save time by processing that with automation, but still having humans in the loop to save time, but also allows us to keep a digital record for exact imagery and data that's used in relation to business decisions and the records of management that are used in there for harvest locations. And the types of technology which underpin this for those that are very keen on their satellite technology are LiDAR imagery combined with near-red infrared imagery to understand the vegetation estimations. This is particularly important not only for harvest locations, but also to combine with public data sets to understand, which we'll go into a bit more detail later, on potential carbon loss in relation to deforestation caused by forest fires or diseases or pests that can occur, to understand root cause analysis. So Can I move on to the next slide? And back to
Thanks,
Phil.
This is one of my favorite images. What you're seeing on screen here is a harvest area provided to us by one of our suppliers in the southern United States. And you can see in red the outline for that harvest tract that's been drawn by a person. And then you can see in yellow the area that the AI has identified by examining the satellite image. And we can see straight away that the yellow line is excluding some things that the hand-drawn image isn't. So we've got a strip running from the top right down to the bottom center of forest that hasn't been harvested in this case, and the AI is able to exclude that. So it can just form its analysis on the areas that have been harvested. And this can be done exceptionally quickly. It can be done not just on a satellite image from today, but a time series of satellite images going back 20 years in some cases. So we can get a good view of how that land area and its usage, importantly, has changed over time under that supplier's observance. Let me pause there. And Phil, I'll pass back to you for the next slide.
Thank you. Continuing from that, one other type of algorithm that we can use with such imagery is pixel level algorithms, which aren't necessarily apparent to the human eye. And you'll see from this image on the left here how it's difficult to see it with the granularity that you're observing any particular buildings or structures. What we can do with AI and pixel interlacing networks, which allows us to use the different color spectrums within the imagery and statistical features to use probabilistic matches for then human validation, is interpret land use change, which wouldn't necessarily be apparent from the image quality from the satellites. Again, this gives us a competitive advantage, but it also then gives a direction to the human validation in the loop as part of this process to then understand potential areas where classification of harvest or land use is not quite as accurate as you may perceive from the original high-level image. I'll just pause there and hand back to Si.
Thanks, Phil. So it's really important, again, to Drax that we're looking after the managed forests sustainably. And one of the benefits of removing low-grade woody fibre and residual fibre is that it should help to prevent forest fires, pest and disease in those managed forests and keep them healthy. But how can we actually prove that claim? Again, AI and satellite imagery make it easier for us to track this over large areas. So what you're seeing on the slide there, on the left-hand side, is an area of forest before fire. And then in the center, the AI has been able to pick out the burnt areas of forest. And then on the right-hand side, you see the overlay of healthy versus areas that have been impacted by that forest fire. And what we can do again over time and over geographies very quickly is build up a picture of how healthy these forests are and whether the actions of our suppliers in removing that woody low-grade fibre are having a positive impact. Back to you, Phil.
Yeah, just like to build on this slide a bit further, Si, because there was an article published in the BBC today around a new satellite that's being launched from the European Space Agency, which has been 20 years in a project pipeline, which we're quite excited by, because that's going to be using long wavelength to be able to deal with some of the challenges that you get with satellite imagery, which is cloud cover and not being able to see below the canopies, depending on the type of imagery that's being used. So this long wavelength will facilitate a better ability to look at the carbon stocks across the world in some of the most treasured and at risk areas of forestry, such as rainforests across the world, and also has a wider application potential as well, to be able to see to the depths of below the depths of the trees to the forest floor as well. So that's super exciting from a carbon loss data set to understand the impacts of climate change and deforestation combined. So moving on, Si and I haven't particularly rehearsed who says what at this stage, but I think my take is AI is essential as an assistive technology in similar theme to many of the other presentations today. It's not to be relied on its own. For Drax, it can help us scale our ability to detect harvest locations and track the origin of biomass and the use of anomalies within that process, which allows us to mark up areas which require human intervention or validation. But it also allows us to understand our compliance and sustainability criteria is being met, and where it's not, what corrective action needs to be done in order to correct such challenges. And as the technology evolves, the process with which we validate and track this data will also need to evolve. And I think there's more opportunity coming, not just around different satellite imagery, but in terms of combining data sets to understand better impacts on biodiversity as well. Have you got any closing considerations as well, Si, please?
I think I'd just say, in terms of the team that I run, data engineering, it would be really impossible to cover all of this data analysis without the help of AI. So over the past 12 months, it's been a fantastic benefit to my team to be able to integrate with these products and not only bring the raw data, the satellite imagery, back into our estate, but also the analysis of that data. So it's helping teams like mine and Phil's cover much more ground than we really would have been able to just a couple of years ago. And I'd end with that. Thanks, Phil. And back to Jasmin. Right.
Thanks, Phil and Simon, for the informative presentation. There are a couple of questions from my ends and from the chat room as well. Let me start from the one in the chat room. Can you extrapolate satellite imaging to strip mining and site reclaiming?
As in theoretically, I think absolutely. That sounds like something which could be undertaken with the right level of satellite imagery and time series data. You would need to obviously determine what the characteristics are for the kind of colorations or the pixel level findings and the thresholds which are relevant to that. What we find is it's even with good quality imagery, it can produce false positives, like in lots of predictive style AI algorithms. But we find the better the data, and the better the results are in terms of what you're able to achieve. But yeah, I think I'm not a data scientist by trade, but I certainly I certainly feel confident in that answer that that is theoretically possible.
Thanks, Bill. You may have touched this during the course of your presentation, but are you able to, elaborate a bit, just say a bit, the level of accuracy or confidence AI can currently provide in tracking biomass origin, and how is this validated?
Do you want to take that one, Si?
Yeah, absolutely. So what we see is that we can get hit rates as high as 80% when the AI has been trained on specific suppliers. In terms of kind of perfect accuracy, that's never going to happen, unfortunately. We always need a process where if the AI is unsure, it can drop out a harvest area for analysis to our local teams, and they can verify the results. But we do see very good accuracy, both on kind of the general site, but it does definitely improve when you train the AI for a specific supplier, and you give it feedback for that supplier on what's a match and what isn't.
Thanks, Simon. We have a couple of minutes, and let me just try to ask one more question. Are there privacy or data sharing challenges when applying AI to biomass tracking, particularly when you're working with a diverse suppliers?
Are there privacy concerns
or data sharing challenges?
So it's a good question. We generally have agreements with all of our suppliers that they must share this information anyway. So to give people a bit of context, Drax is a member of a number of different voluntary sustainability organizations, but it's also very heavily regulated by federal and state governments in North America on the fiber that it takes. And so either by law or via the contract that we have with the supplier, this information needs to be shared anyway in terms of the location of those harvest tracks. So we can then quite comfortably apply the satellite analysis to those areas.
Thanks, Simon and Phil. This is an emerging and relevant field. So thank you very much for coming on board and sharing your experience with us. Thank you very much.
Thank you.
Right. Our next presenter is from Class 6.ai. Do we have Anya Chevelp in the room, or Eric Redmond?
Yeah, I'm here. It's going to be me.
Fantastic, Eric. Eric is going to speak to us on AI use cases for CCUS permitting. The floor is yours, Eric.
Yes, thank you. Appreciate it, and thank you all for having me. Had you told me a year ago that I would be giving a talk to a group of geologists, I would have said no way. My background is entirely in digital technologies, although my background is largely in sort of heavily regulated industries like healthcare, and I work for the USDA and all of that. But I'm also the founder and the CEO of Classic.ai. I'm also an author, and the funny thing, this book, Deep Tech, came out 5 or 6 years ago, and I was really trying to push this idea that, hey, AI is something important and you should pay attention to it. And that's been largely my background, has been about how do we improve workflows using data and now AI. Now, I do want to start off by making one thing very clear. AI, I do not believe, is a replacement for human judgment. You'll hear a lot of folks, and I've loved all of the talks in this conference so far, because I think people have been reiterating that that this is not about automation. This is about acceleration. And a format like this is very hard to try to be funny or tell jokes or anything because I have no idea who's on the other side of the screen. But I did find this amusing. In the software development world where I come from, there is now this growing concept called vibe coding, and it's this idea is I don't need technical people, I don't need experts. I'm just gonna use AI to generate code. And this on the right is a tweet from a guy that it feels like a play in two acts. It's like step one is extreme hubris, and then the denouement is basically, hey, it turns out that experts might be useful after all because this guy was getting attacked and he had no idea why. But anyway, into the permit side, the relevance here is really, and again, this is focused on U.S. economy, but we see similar trends globally, which is there is far more interest in our area of focus, which is digging Class 6 wells, than there actually are approved active wells. And a big blocker to that is permits. Now, this is a permit, right? This is actually a photo that a friend of ours took. It was a 21,500 page Class 6 permit being submitted to the EPA. And he was talking about how, oh man, this was such a hassle to write. And all I could think is, oh, that poor regulator, like who's got to sit down and read this thing? And the reality is when you look at now this top bar, this is the EPA's own coloring scheme where they say, hey, here are all the stages in submitting a permit with preparation and filing, completeness review, all the way down to preparing the final permit for approval. And two giant chunks of that are merely uncovering deficiency, either responding to notices of deficiency, meaning that there are portions of the permit that has been submitted that aren't there, which seems like a very simple check. But again, when you're talking about thousands of pages, you could easily overlook and miss a section, all the way to responding for requests for additional information. So after the technical review is happening, it's like, hey, you're missing something. And so AI is fantastic for this. And in fact, I think about it in the same way as in the 90s and early 2000s, how AI was used for discovery in legal cases, where there are all this paperwork, all these emails, and let's just let the robot sift through that. And so in order to do a completeness check of a permit before you send it in, that could, because that responding to notices of deficiency could delay your permit by weeks or months. And so just having an AI check it and say, is it everything I expect to be there? Yep, great. That could save you a lot of time, which could save the economics of the project. The second part we've been using AI for is consistency. And so multiple people are part of writing one of these permits, and they all might use terms differently. I mean, if you find 10 people and ask them to define area of review, you're going to get 10 different definitions. So how do you align all of the people involved in this process on some consistent terms, some consistent definitions, some consistent measurement? If somebody, one person says, I'm going to measure well pressure by an average, and another says, I'm going to measure well pressure by what's at the very bottom of the well, you're going to get two different numbers. They're going to be inconsistent, but they're both be correct. And so a reviewer might say, why are these numbers, why do they not align? AI can call that out pretty quickly. And then finally is just correctness. Like, are the claims you're making not only cited and correct, but are they logically, do your arguments logically follow from the premises? And so this is something else that certain kinds of AI, like the kinds, we're digging into, are actually pretty good at. ultimately, I think, and by the way, the things I've mentioned, if you notice, have nothing to do with generative AI or anything like that yet. But I do think that we can, after we've uncovered those deficiencies, we can then accelerate the effort by using AI to support research. Because so much of your job when writing a permit is just looking up information. So anything that can streamline that is hopefully a very good thing. Ultimately, I mean, you know, I would like to get to the point where we are able to generate aspects of the permit, although I see that as down the road. And then maybe even aspects of permits could be approved. I mean, when you're an approver, you know, 95% of a permit could be pretty boilerplate, pretty basic stuff. And what would be great is an AI that can elevate that 5% or 10% that's actually critically important, and draw their attention to that. This is a sort of an example of the system that we build out at a high level, or we're building out at a high level. And the thing you'll notice, hopefully right away, is not very much of it is AI. The pink areas, we've got parts of AI that tie this whole thing together, but really most of it is just plain old data management. We've got data sources, and then we have to correct and clean up that data. And so in some ways, even though we're class 6.ai and we're big believers in the value of AI, really we're a data management and data governance organization more than anything. And I think that if anyone is in this space and they are transparent and honest about what they do, they would probably say the same thing, that still 90% of their work is making sure the data is good. Now, I wanted to throw this up because this actually was just published really recently. This came out of MIT. And I would recommend kind of glancing through this, although it is deeply technical, because the one thing that I think is really interesting about this is, even though, and by the way, I am an expert in this space, I live in this space, and I find myself drowning in the fact that there are new AI models that seem to pop up every week. And how in the hell are you able to keep up with that constant change? Well, this is actually a very good framework, and what they've discovered is that there are actually there's sort of a common equation that underlies all of these, all of the AI models that are popping up. And if you can categorize them, and if you can categorize them, and you can start wrapping your head around, okay, is this a fundamentally new thing, or is this just sort of an improvement on something that exists? And so the reason I wanted to throw this up is, even though it might seem like there are hundreds or thousands of AI models, really, there's not that many. And most of them aren't going to apply to your particular interest or area of expertise anyway. Or they've been around for, you know, decades. I mean, K-means came out like 50 years ago. So I am going to focus on just sort of a short list of AIs that we found that are relevant for this process. One, high-level natural language processing. This is what we're talking about at the end of the day, is text, which includes things like large language models, which themselves include things like GPTs, like ChatGPT, but also diffusion models. Small language models, which I don't think are talked about as much, but for us, this is actually a very critical component and feature of what it is we're building. Optical character recognition. So again, you know, you've got scans of papers. How do you actually convert that into something that is readable by a computer, whereby then you can search for it, again, if you're talking about doing discovery and research, or that you can use to train models, that you can use to train these LLMs. I don't think you should overlook classifiers either. Classifiers I find very helpful, because especially in our case, where we've got multiple small language models that are effectively trained experts for in different areas, whether that's geology, or whether that's finance, or whether that's the law. When you ask it a question, you need a classifier that can sort of direct your question to the right expert. And then finally, neurosymbolic AI, which I I wouldn't be surprised if a majority of you haven't heard about. And really what this is a form of AI that converts, rather than LLM, that's sort of this giant neural network, it leverages neural networks but codifies things into first order logic. And the nice thing about that is that suddenly a lot of your AI is actually explainable and also editable. So you can see immediately whether it's making correct logical conclusions based off of the premises that it's assuming. And also, and I think this is an important thing, is I mean, thinking about AI as a general purpose learning tool. So again, writing a permit requires a broad collection of skills and expertise. I mean, you might be a geologist, but you are probably going to be asked questions from a lawyer. You're going to be asked questions from, an investor, a financier. And so I find it actually really helpful to really help wrap my head around areas that I might not be an expert in and add structure to those areas of exploration. And I also find it really helpful to quickly communicate thoughts and ideas, again, using their language rather than using your language, which just helps aid in that communication and helps, it might not be perfect, but it's good enough most of the time. So I love focusing out. I mean, look, there's a lot of problems you have to think about when you're adopting AI. Accuracy and completeness of technical information. In the previous talks, I heard this called out a lot. Hallucinations are a real problem. And in fact, it's getting worse. There is now a growing area of research that's showing that these large language models like ChatGPT, the more data we dump in them to train them, the more they hallucinate. Their error rates are actually going up the more data. And it's contrary to what people have assumed up until now, which is, hey, if we give them more data, they're going to be smarter and be more correct. Actually, we're finding the opposite is happening. Regulatory legal compliance, again, you can only train based off of what's written down, but there's a ton of knowledge out there. I mean, if you're a permit approver, a lot of it might be just your preference, or there's a lot of implicit knowledge that might not be written down. How do you train against that? Explainability and auditability. This is a human problem. Credulity in the face of extreme confidence. There is a measure of self-driving cars from class 1 to class 5, class 1 being fully manual, class 5 being fully automatic. And a lot of research has shown that the class before class 5, where it's fully automatic, is actually the most dangerous, and it causes the most accidents. Because when someone believes that there is someone else at the wheel, they tend to stop paying attention. And so when you have these AIs seeming extremely confident giving you answers, people tend to switch their brain off and say, well, that problem's solved, when that actually is the time you should be doubly or triply validating those assumptions. Another one is data quality and availability. Data is often sparse, incomplete, or unstructured. That's just always going to be a problem. That will never go away. And then these are very energy hungry models. I mean, these AIs, I think we all know, you've got these major players like Google, like opening up they're trying to create new power plants. And so it might seem counterproductive if our goal is to be reducing carbon. Why would we be using models that might actually increase carbon emissions? So I do think that there's some solutions to these problems. One, to the point about hallucination, not all models hallucinate. So for example, I brought up neurosymbolic AI. Its structure is not a hallucinating kind of a structure. It's just a logical graph of a knowledge graph, and will output conclusions. You might disagree with the conclusions, but you can always validate because it's very explainable. Capturing that implicit tacit knowledge is not impossible. You just have to build it as a core feature into your process. Unfortunately, you can't really fix humans, but you can create feedback loops that prioritize attention. So, I mean, kind of thinking about like the self-driving mode on Teslas, where they're like, hey, you've got to have your hands on the wheel. It won't stop accidents from happening entirely, but it can dramatically reduce them if you create those right sort of mechanisms. Data quality, I don't have a way to fix this. There's always just going to be an issue with data. But again, and that's why I say that for our role, we're largely a data management and governance company, because that is the crux of the problem. Most of these other problems have solutions. And when it comes to power hungry, like, again, don't sleep on small language models, because they actually can be more accurate, more precise, and much less energy inefficient. So a few final thoughts I wanted to close out. One, there are tons of these Class 6 permits currently in review in the US, but only about a dozen projects have actually been approved and are being developed right now. And it's beyond Class 6. There's a ton of projects that are in the exact same boat. It's heavily regulated industry. We have all these permits that we have to get through. They can take years to get through that process. And if we can accelerate them, then that just means more projects and more work. And especially if it's good work. I mean, our very area of focus, even though we say Class 6, is really on this sort of accelerating decarbonization. Yeah, this, again, I do want to call out back to how I started. I do think that humans should be making these critical judgments, but not spending their days fine-tuning verbiage. I like to ask people, did you become a geologist so you could do paperwork? Probably not. And so, great, let's use these tools. Let's use AI to automate it as much as we can. That's it. That's my talk.
Yes. Thank you, Eric. An interesting presentation. A few questions for you. Can you please expand on the role of AI in helping experts in different fields talk to each other with project development and financing in mind?
Yeah, absolutely. You know, actually, I'm gonna pop back up to this slide. This is kind of a example of what I was meaning here. So if you kind of look at the upper right, this was me using Claude and saying, hey, look, permits are huge and they're complex. And I'm the first to admit that I'm not an expert. And I needed to, and I didn't need something perfect to understand it. I just needed a framework in which to think about the types of data that would appear on a permit while I'm speaking to the experts we have on the kinds of information you're going to need. And so you can do the exact same thing where, you know, and I use multiple models here, where you can go into, let's say, Google Gemini and say, I need to talk to an accountant and the accountant is using terms that I don't understand. Can you give me a high-level crash course in accounting and explain it to me in 5 minutes? And it will. It'll give you, and it's pretty good. It doesn't have to be perfect. And then you can take that and maybe go to Claude and say, hey, can you give me a visualization that's going to help explain, you know, maybe what the accounting equation is that and why assets equal liability plus equities or something like this. And just a little bit of that back and forth. It's almost like having a friend that's an expert, and that you can just ask them questions and then use that as a frame of reference to have an intelligent conversation with an expert.
Thanks, Eric. We're out of time. Can you respond to this just for a few seconds? How adaptable are these AI tools to other jurisdictions beyond the US EPA, especially where permitting requirements differ?
Yeah, absolutely. And
just a quick one. We are out of time. Yeah.
Oh, sorry. You wanted me to pick a question?
No, I was like, can you be a bit fast in answering that question, because we're a bit of time.
Yeah, for sure. I mean, the fact is they're super similar, right? I mean, what you're talking about ultimately, if you think about it, is sort of a graph of data that we need to put into a linear format, which in that linear format we call a permit, and a narrative form. And so that doing that translation, whether it's an EPA Class 6 permit or, you know, really any other kinds of permitting structure, like that's kind of what AI, I think, excels at.
Thanks, Eric.
Great, thank you.
Very well. We're going ahead with our next speakers. We have John Curtis from Petrolink in the house, and Bertrand Rioux from Net Zero Metrics.
Thank you, Abdul'Aziz. You've obviously never been to Canada. It's pronounced Roux, actually. It's a French name, but never mind.
I apologize for that.
No problem at all. I'll share the screen right away.
Very well.
Please let me know when you can see the screen.
We can see a screen.
Thank you.
You're welcome.
Good day, everybody. I'd like to first give my thanks to Abdul'Aziz, Jasmin, and the IEAGHG and their sponsors for the opportunity to share our thoughts on the future role of AI, and specifically.
John?
Yes.
Yeah, we can see two screens. We can see a smaller one at the side. My thinking is that you do not wish to share the second screen.
Okay.
Yes, we can see it right now. So if you can put it on presentation mode, please.
Yep.
Fantastic.
Is that okay now? Abdul'Aziz, is that okay?
You need to click on the presentation mode, John.
Okay. How's that?
Fantastic, fantastic.
Thank you. Just again, I'd like to thank the IEAGHG and the sponsors for the opportunity to speak about our own use with AI, specifically talking today about retrievable augmented generation, commonly referred to as RAG. I have a background in the energy industry, geotechnical data management. We're in the middle of an energy transition. In the last few years, we've also been involved in CCUS as an essential role to play as part of the energy transition. And my colleague, Bertrand Roux, has been involved in carbon accounting in the last few years, and we're working together with AI platforms, which we call Agent George. The reason for Agent George, by the way, it goes back to the Second World War, when there were automated controls for aeroplanes, and this automation, which is of course still in use today with mechanical automation, still in use today in aeroplanes, was called George because of that was the King of England at the time of the Second World War. So we're in the channel for supply chain, and there are two supply chains around CCUS. There is, of course, the physical supply chain, which is the production of hydrocarbons into various facilities, and now the effort to capture emissions at source, and then to re-inject them, often down into the same reservoirs. In the Dutch sector of the North Sea, there are a lot of depleted reservoirs, and those very same reservoirs are now being repurposed, or considered to be repurposed, for the injection of carbon dioxide taken from the facilities, or indeed taken from third parties that with the CO2 that travel on a common pipeline injection platform for the injection into the well. And therefore there is the whole question of carbon accounting with the preparation towards the monetization of that process. So you'll recognize the part of the curve on the left. It's the famous broomstick plot, where we come to the emissions. Emissions are still generally rising, or expected to rise at the moment for a few more years, and then we reach peak emissions, and then there is a decline, hopefully, according to the Kyoto Protocol, which was signed up to by most of the countries in the world, down to what is termed net zero by the year 2050, although some countries have adopted different timings for that. So CCUS has been identified as not only a necessary way to offset emissions, but also it is actually going to be a significant business in the future. And as you can see here, and as you can find on the internet, many companies are now engaged in the CCUS marketplace because it does represent a significant business opportunity. Quite a lot of the people I speak to confuse net zero with gross zero. We can't go back to pre-industrial levels of carbon dioxide. What we have to do is recognize the fact that certain industries, like the energy industry, cement and steel, will not be able to decarbonize completely, and they will have remnant emissions, residual emissions, which are almost impossible to reduce any further. And at that point, to reach their net zero targets, they have to be in a position that they're offsetting those residual emissions against sequestrations. We've heard about biomass today. Most of the people are joining around subsurface emissions in the conference today. There are many ways in which this can be done. Go plant some trees in your backyard. Every little bit will help. So when it comes to assimilating all of the information for subsurface sequestration of carbon dioxide, we are going to require geotechnical planning data. They have to look at the risk, and we've heard from speakers earlier today about quantifying risk from either repurposing existing reservoirs which are depleted, which of course have held those hydrocarbons for millions of years, and therefore you should be capable of storing emissions. And then once that is done, we have very complex mechanisms that need to be put into place. We heard earlier on from Shell representative about digital acoustic sensing, digital temperature sensing, where we're monitoring the bloom and how quickly the bloom is growing, and of course whether there are any leaks. So in the CCUS workflows, we need access to and experts who have knowledge of subsurface data. But at the same time, we need to have knowledge of carbon accounting, the sequestration accounting. The diagram on the left shows a project for a field in the Dutch sector of the North Sea, which this year is being switched from production to carbon dioxide sequestration. So it's using existing infrastructure and it's being repurposed, which will obviously reduce the cost of sequestration. There are many stakeholders involved. Both Bertrand and I work in data management, and data security, of course, is one of the primary concerns. How is this information made available to stakeholders? How is it made available to regulators and other third parties who have a right to that information? We heard just now from one of the speakers about nomination and confirmations and permitting. All of these are taking a long time. There are shared transportation pipelines. So companies are putting carbon dioxide sequestrations into a shared resource that needs to be monitored, mass balance analysis, a lot of impurities, contractual obligations to maintain impurities, different types of gases which might find their way into the carbon dioxide stream. We have sensor real-time data. The carbon dioxide coming from one particular company will need to be monitored for those impurities, will need to be monitored for the volumes, and all of that then has to be independently validated if it's going to be moved to monetization. I mentioned that in the previous slide that ExxonMobil see a $4 trillion market. That will obviously require that monetization of the credits where CCUS is provided as a service will obviously require validation by specialists in that field. So carbon balance sheet is important. I showed the budget. There is a budget to reach net zero of about 500 billion tons of carbon dioxide. Emissions are going to continue. Emissions need to be monitored as part of a company's net zero obligations, their scope 1 emissions, and then what are they, if there's a company, an energy company that's involved in carbon capture and storage, the sinks that they're able to create, those sinks may not necessarily be technologically based. Many of the energy companies are also purchasing nature-based offsets at the moment to help in their move towards their net zero obligations. And then there is the whole question of the monetization. How will this be done, whether it's biofuel or whether it's by sequestration, the monitoring of forest, as has been mentioned by the speakers before me today. All of this is part of the carbon balance sheet reporting, which is going to need to be done. So Bertrand and I are very active in two open group forums. The first has been going for quite some time, 10 years. It was originally called the Open Subsurface Data Platform. And this was an effort by major companies in the energy industry to try and break down the problem of data silos, which was mentioned earlier today. The problem of data silos exists not only between companies that need to share information as partners in a particular project, it actually exists within companies that are so large and have data sets which are protected. And how are we going to share this information either inside the company or between companies? And the OSDU was set up and is currently active with over 300 industry members to build a system whereby all types of subsurface data can be put in a single model, and it's been designed to be cloud native and therefore is AI ready. Another open group initiative is the Open Footprint Data Model. This was set up to be not just specific to the energy industry, but in fact to be a model which could be used right across industry to manage and transform this data, to store it, and then enable it to be shared between different stakeholders who need to share that carbon accounting information. The two forums got together about 2 years ago and created a harmonization project because there were obviously a requirement to manage and monitor subsurface data, and also the carbon footprint monitoring and how that could be stored and shared with other people. And this CCUS harmonization project is very active today, and it incorporates subject matter experts from different parts of the subsurface universe, seismic, reservoir, wellbore, these so-called domain data management services, which are built by and supported by subject matter experts in those areas. And then probably the most important in the early days is the production DDMS, where we're looking at the transportation of fluids. That originally was set up, of course, for hydrocarbon production, but it's possible to repurpose that for carbon dioxide compression, transportation, and injection into the subsurface. In particular, as I mentioned, this production data management using models which have been developed by other open standard groups in the energy industry, which can then be repurposed as a reporting entity for the injection and monitoring of subsurface data. We are data management companies, and data ingestion and consumption, as was mentioned also by one of the speakers, is really the problem today, particularly when it comes to the use of AI. We've got data that comes in from anything from, it was mentioned before, microseconds, all the way through to one particular value a year, which might be a scope 1 value for a company, or it might be the total sequestration that has been purchased or managed by a company, which is then reported to a regulator. So this data covers a vast array of different types and frequencies of information, and we need to find a way in which this can be stored in a consistent format so that the different stakeholders can access that according to well-defined access control lists and legal right of access to the information across these data silos. So I talked before about the physical supply chain. I've just been talking about the virtual supply chain, which is the data itself related to the different types of facilities. Here at the bottom, we're talking about drilling rigs, injection facilities, but it could also be cement plants or steel manufacturing facilities. And the use of these open standards, which are being developed by industries, to find a way to aggregate this information and then make it available to the people who need to see it, stakeholders, financial institutions, credit rating agencies, those people who may wish to see proof of the sequestration process when it comes to monetization. So how can AI, and in particular generative AI, assist us in this virtual supply chain? Almost all data systems today suffer from the middleware problem. The middleware problem has become worse. If you have information that gathers data and you wish to send it to people who wish to see the data in some form of system of record, you have to translate it between the two. APIs exist to enable this to be done, but quite often the data has to transfer across security barriers. And in those cases, often a middleware is used. In the case of the OSDU, as I mentioned earlier, they are building a type of middleware solution which enables the information to be gathered from microseconds through to very low granularity information, which is destined to a system of record, which helps to monitor and then manage and prepare the carbon accounting for the CCUS process, which is required as part of the monetization or the regulatory framework. Can AI help us in this challenge of gathering all of this data and putting it through into the system of record? So I'd like to introduce my colleague, Bertrand Roux. Bertrand, are you there?
Yeah, hi, John.
Yes, perhaps you could just go a little bit into how we might be able to use ETL, extract, transform, and load, using IEAGHG to populate these types of systems of record. In other words, in the first instance, how can AI help us with data ingestion, Bertrand?
Yeah, thanks, John. And let me just set some context. So John has set the stage right for a data platform. We've been talking about these open group platforms, OSDU, and the Open Footprint Forum, or the Open Footprint Data Model, to consolidate data, right, that can be used by both humans, but also AI in assisting those humans, right? And there are a couple things that need, in order to leverage a platform like that, one needs to, streamline the ingestion of data, the loading of data from disparate sources, that can then be leveraged by both humans, but also AI, right? So streamline and accelerate, right, workflows and specific tasks. Right. So one thing we've been looking at, right, is leveraging both generative AI and tools like RAG to assist in this process of extracting information, transforming, and then loading it into the ETL. Now, loading it into the integrated platform. Now, this can be done, right, with traditional systems, traditional data management systems. Several of the presenters in today's workshop mentioned, AI plays a role here, but often it's just in certain areas or aspects. Right? It's not implemented across the system. We're not relying heavily on AI, but on ways that AI can assist in specific stages. The same applies in the ETL, right? So this may include right, identifying in your initial extraction process patterns, right, in your source data from various companies or data suppliers into your standardized data platform. And then once that data is mapped, right, there's some validation and quality issues in the final recording or loading of that data, right? And we've been looking at the role of AI in identifying, right, those potential issues and iterating over this process of the ETL to assist humans, right, in ingesting data into these unified data models. Yeah, John, you want to continue?
Yeah, thank you.
Yeah,
thank you. Yeah, so we've covered data ingestion, so we can bring data ingestion into a platform. I should have mentioned that the platform, which is being developed by companies within the OSDU and the Open Footprint Forum, this is all open source, and so therefore these tools are available, and the objective is to build a platform which could be used by multiple industries to exchange data in a consistent way according to particular schemas that are being developed for the particular types of data. So what about the other end of that, Bertrand? So we talked about consumption, we talked about ingestion of data. What about the other end? We need to get that information to the people who need to see it. In other words, the consumption. How about the system of record, which then could be used for consumption?
Yeah, so I won't go through this slide in detail. Actually, a big chunk of this slide is dealing with that ingestion assistance from AI. But then there's the second point, which is supporting core applications. We've looked at several areas, whether it's real-time processing and assisting in getting data loaded into a unified data model, right? To monitor real-time processing data, which is crucial, right, in these CCUS as a service or shared infrastructure or systems, right? It can become quite complex as these systems scale out, right, to bring down the cost and scalability of CCUS, right? We're still far from that point, but we're working towards it. Now, a common concept that's talked within the energy industry is establishing these digital twins, right? Now, this requires consuming data across a range of supply chain components, right? In whatever system you're looking at. In the case of CCUS, for your carbon capture units, your transportation units, and then finally your geological storage and injection sites, providing a unified data platform, or using a unified data platform can assist in loading data or supplying data to that digital twin to provide, a traditional, real-time optimization and analytics, but also, using AI to assist in identifying patterns and potential optimization strategies, right, within that digital representation of your infrastructure. And then obviously, right? Yeah. Go ahead.
So I think, we're running a bit tight on time, so we might just want to very, very briefly run through the types of technology that the people on the call might think about when they're looking at their own data supply chain, the virtual supply chain for CCUS, in order to streamline the process. Just a few final comments on that, Bertrand.
Yeah, so we're building sort of these agentic frameworks and leveraging various tools to demonstrate these capabilities, whether it's ingesting data or consuming data. So obviously, I've already mentioned we've been looking at the role of RAG to help extract information from documents and identify patterns. Also connecting our agents to the relational databases or the unified data models that we've spoken about, so that AI can access and connect this data and perform certain, or assist, right, real people in performing certain actions, through prompting and so on. But also, looking at integrating sort of the structure into the way the agent is performing certain tasks. And the reason we do this is to create this consistency. So AI, where we do use it, when we do see a value in using it, can be easily integrated, right, into consuming applications by providing this structured response. So we don't need to go into more detail on these technical aspects, but these are the tools we're looking at building.
Thank you, Bertrand. Abdul'Aziz, I think we've probably come to the end of our particular presentation. I'll stop sharing now.
Thanks, John, and thanks, Bertrand. Well elaborated presentation. Unfortunately, I'm sorry we do not have any time for questions at the moment because we've literally run out of time. I will thank you very much. I will quickly now call on Jerome from Demitrix. Jerome, are you in the room?
I'm in the room, yes. Can you hear me okay?
Fantastic. And Jerome is going to speak to us on AI-powered activity-based GHG emissions calculation. So the floor is yours.
Thank you.
Welcome.
Can you just confirm if you can see my screen? I assume it's good. All right. Hi, everyone. Thanks for having me. I'm Jerome, the co-founder.
I cannot see your screen.
Not?
Yeah, I can see a screen. Can you kindly put it on? Yeah, fantastic. All good.
Does it work now?
It does work. Thank you very much.
I assume there's a slight delay, so apologies. Anyway, thanks for having me. So my name is Julio of the startup The Metrics, and we aim to unleash sustainability metrics. A few words about myself. I'm a mechanical engineer by education, and I've launched The Metrics together with two co-founders in the finance field and also carbon management to help companies better estimate their Scope 3 emissions. So what we do, we automate lifecycle estimations of a company's purchased products. The problem we're solving is that we help corporations quantify GHG emissions using the activity-based method. This is currently a huge pain for sustainability officers. Why? First, because of complexity. Sustainability teams are overwhelmed by thousands and thousands of data points to accurately calculate Scope 3 greenhouse gas emissions through an LCA for all the purchased goods. The data quality they have is unfortunately very low because they use ERP systems that were not designed for that purpose. They were built for procurement or for finance, and now they look to get this data, which is somehow structured, and use it to perform life cycle assessments on these base products, and this way have an activity-based calculation method. And all this leads to very high costs, and this is why we're here, and our solution aims to help quantify GHG emissions in a simple way using AI. So the simplicity comes from the automation. We automate the Scope 3 activity-based GHG emission calculation using our different algorithms. These algorithms are used to enhance the data quality given from the ERP systems to identify how well this data is suited to perform lifecycle assessments. And all this finally helps to reduce the costs because of a streamlined approach. You put ERP data in, we analyze the quality of the ERP data, we enhance the quality, and then we conduct activities to help us get the data that is missing using AI. So here an example of how it works. So we start with an unprecise product description. That means a company, for example, purchases a phone. All they know is that it is a phone, but now they want to estimate the Scope 3 emissions from the phone. What we do is that we reverse engineer the items they purchase. So we live in a world where not every phone has a product carbon footprint. So obviously someone needs to do the work. And so we reverse engineer those different products. So we have a breakdown of the different components. So we look for materials and then we go after the weights of these different materials. And then further, for each of these components, we estimate and we approximate the different life cycle stages so that we can then plug to LCI databases and help companies estimate on a product level the Scope 3 emissions. This is massive because we do this for the thousands and thousands of products a company purchases to finally help sustainability teams solve their Scope 3 challenge. So here in a table view, if you're in a sustainability team, you might look at many tables. So usually you start with an ERP database. What we do is we clean up the data. So that means before you had maybe a column in which you had the name of the product or the material purchased, some units, and then some other metrics. So we help split this up into material, product, quantity, unit. Then we map this one with LCI databases to help us identify which activities or which material footprints lie behind these parts. And then we also go and chase down additional information from bills and invoices on the scope 3 emissions on the item level. So an example of some technology parts we're using, if there's a document from which the data was not captured yet, then we would run an OCR analysis to extract information from the document. So here an example from a receipt. And then once we've extracted this information, we have everything in a structured manner, and which helps us then start of a purchase through the part or the invoice and receipt that was linked to it, to break it down into the different subcomponents and then do the mapping to allow an estimation of the CO2 equivalent emissions. This is our team: engineering, finance, and carbon management. And here an opening, because of CCUS, there's a lot of technologies and projects that are being launched, but we wanted to highlight that it makes probably sense to look at the emissions coming from all the components that are needed to build the infrastructure and the hardware, to see when the system is actually able to capture more than it emits. So that was pretty much it from my side. So thanks for your attention, and if there are questions, feel free.
Thanks, Jerome. That was informative. Thank you for your presentation and sharing the contents that you've just talked about. So on this note, I would like to say what an incredible meeting this has been. There is a lot to unpack, and I would like to seize this moment to thank all our speakers for sharing their expertise, and experiences. This is very much valued. On this note, I would like to invite my colleague Jasmin to close the workshop. Jasmin.
Yes, thank you, Abdul'Aziz, for moderating this afternoon. Yes, we would like to thank you all for attending and also contributing to the discussions with a lot of good questions. Unfortunately, we were running a bit short on time at the end, but please feel free to connect with us and also with the speakers. We have been asked whether the recording will be available, and it will be available sometime after the workshop on our webinar website. I've dropped the link for that for you in the chat, but we will also approach the speakers if they are willing to share the slides, and then we will come back to you by email if we have found a way when and in what format those slides will be available. So with this, I would like to thank you. My main takeaway from this day was definitely that AI is a tool that we can use to speed up our work, to make our work better. It will not replace our work. We will still need to critically discuss what the AI has put out for us. And yeah, with this, I would like to thank you all and wish you all a pleasant rest of the day. Goodbye.